Hello, welcome to a slightly weird live stream. My name's James, and we're on a quest for the Quintic. This is a maths education kind of thing. My plan for this week is that I want to get to the Quintic. I want to understand the Quintic, and I'll tell you what that is in a second. I'm putting it on Twitch as a sort of weird experiment. I don't think anybody's going to watch this, but that's okay. Because at the end of the week I'll have found my Quintic, and that's all I need. Here's a kind of map of what I'm trying to do. Let's see. So I've got a pointer, and then also good. Okay, so we are here, over here. Ooh. Would help if I selected a pen, wouldn't it? We are. Come on. We are over here. And the quintic that I'm trying to get to, the fifth degree polynomial, is over here. So this is like some sort of mountain over here. Quintic. And in between me and understanding this fifth degree polynomial, there's a whole bunch of theory that I need to try and understand during this week. The main thing is this kind of mountain range between me and understanding something that I technically did at university but never really understood, which is called ring theory. So we've got rings over there. There's a related topic, there's a kind of nearby area. If I draw some sort of like maybe some sort of river marsh down this side, so sort of river over here, out to the sea. What do rivers look like? There we go. Coming down from the mountains, I suppose. It looks more like a snake. No, never mind. Over here, modules, which I think are not going to be on the way to the Quintic, but it's kind of this related topic between me and over there, and that fifth degree polynomial fact. On this side of the mountain range, things that are a bit more familiar to me, we've got things like group theory. That's like some sort of lovely forest over here, full of, I don't know, elves or something helpful, which are going to help us on our way through the mountain range to the Quintic. And also over here, we've got sort of like vector spaces, which I don't know, some sort of like mine full of dwarves or something. And the plan is that we walk, with the help of group theory and vector spaces, things that I already know from there, we walk, walk, until we get through past rings into this space out here. Now this space out here is Galois theory, which is some absolutely brilliant theory that I'd really like to understand. Invented by, in the first place, Évariste Galois, who's an extraordinary mathematician. There's loads of stuff in there, and my map's a bit vague at that point, but hiding out there somewhere are things like field extensions that I'll need to understand. So that's like some sort of lake full of lava or something that I've got to go, I guess, through and around. And then out here there's like some special like radical extensions and like splitting fields, which now these are just words that I don't understand at all yet. We need to do that so we get to the Quintic over there. This is the quest I'm on, thing I'm trying to understand. The fact that I'm trying to get to, the fact about Quintics over there, is that you can't always solve Quintics using addition, multiplication, subtraction, division, and radicals roots, like an nth root. In a way, you can solve quadratics. You know, the quadratic formula has a big square root in it, and that's fine. There's a cubic formula, there's a quartic formula for fourth degree polynomials, but somehow Quintics are too weird. There's something different about fifth degree polynomials, which is why they can't be solved. Which the thing I'd like to try and understand this week. Okay, so if you're coming with me on this journey, then most of it is going to be marching through rings and trying to make headway through Galois theory. Um, I'm not starting from nothing. I already know some stuff about group theory and vector spaces, but just a tiny bit. I learned quite a lot a long time ago, and I've forgotten more of it than I would like to admit. Along the way, if I think we're using some group theory or vector spaces, I'll try and be really clear, so that it's not too mad along the way. What you're probably thinking is, why can't they just take an eagle and go straight to the Quintic, right? Why can't they just go straight there? I mean, most of this stuff is going to be aided by lecture notes from the Oxford Maths course, and the lecture notes just exist. I've got them on here. I could just go straight to the Quintic, and actually I think I might do that first, just to demonstrate what I'm up against. So let's go to the Quintic. Let's have a look at that. So I need to go into Galois theory. Here's Galois theory, some lecture notes from Damien Rosler, which I've taken from 2022. These are on the website. If you want a link, on my Twitch page, there's a homepage link which takes you to my website where you can get a link, or you could just search for Oxford Galois theory, to be honest. Right, so the thing I'm looking for is really near the end, so I need to go all the way to the end of this 43 page document, and I think the thing I'm looking for is around here somewhere. Splitting fields, insolvable quintics. Right, this is the fact I'm going for. Hi, Feelsley. There's someone in chat. Hello. We're looking at some Galois theory. We've got down to some group facts and insolvable quintics. Well, that's a lie. I've jumped straight to the end. So, oh my goodness. So the exciting thing for me is that right near the end of this quest, there's going to be some group theory. It's that kind of familiar stuff, the elves in the forest at the start, comes in right near the end. And in here somewhere is the proposition. No, this is about there being an irreducible polynomial. That's not interesting to us yet. Down here, there's a fact. So here is the thing that I would like to try and understand this week. This thing. This is the goal. So it's a fifth degree polynomial, x to the 5 minus 6x plus 3, and it's a member of, it's in the set qx. We'll learn what that means soon, and the fact here, corollary is another word for consequence or fact, is not solvable by radicals, and I think by radicals means the nth roots kind of thing, and the proof doesn't make any sense to us yet, of course, because you can't just jump to the end of the quest. So it says polynomial is irreducible. We're not really sure what that means yet, by Eisenstein's criterion. We can go look that up, I suppose, but not sure what that is yet. Furthermore, we compute, and then they're checking this sign change, and the limit goes to infinity, the limit goes to minus infinity, so it's got 3 roots. Okay, it has at least 3 roots. So furthermore, then they find the derivative of this, and the real roots of that are something. So they're talking a lot about, that's the Galois theory, right? If p of x had more than 3 roots in R, the polynomial would have had at least 3 roots in R by the mean value theorem. So this is like some analysis thing. So it's checking that it has exactly 3 roots, which is important for some reason, I suppose. And now here comes all the Galois theory, and the reason we just can't just skip to the end. We can thus conclude from proposition 6.5, which is further up this page, that the Galois group of P, I think, is isomorphic to S5. So, goodness knows. Proposition 6.5 sounds pretty important. Since S5 is not solvable, a word that we haven't met before, see the end of subsection 5.3.1, we conclude from 5.18 that p of x is not solvable by radicals. So it sort of can't just skip to the end of the quest, right? Because for that to make any sense, we would need to understand proposition 6.5, theorem 5.18, 6 from 5.3.1. We have, as it stands, no idea why they're checking that it's got 3 roots in R. That makes sense to me that this thing's got 3 roots in R, I guess. It's kind of up and down and up, but that's not really engaging with what's going on, right? We don't know why this is being checked yet. Now, we've got a choice. So to try and understand why this is true, we could work backwards. We could go back to proposition 6.5, but I think it's going to get worse and worse as we go backwards. I can see above here, oh my goodness, complex conjugation is a field automorphism of C. I can see that as we go backwards it's going to use quite a lot more things. The journey is quite a lot of stuff in the middle. In particular, there's like Galois of L, vertical line Q. So what I'm going to propose instead is that we spend a bit of today, first day of our quest, trying to work out the kind of overall picture a little bit more, and getting started on the kind of ideas about these objects, which are rings. I think what I want to do is build up some examples as well, so that we've got a sensible example space. Why are we doing this? Well, genuinely want to know about quintics. Galois theory is also useful for other stuff. I haven't decided yet if I want to learn all of the stuff or just enough stuff to do quintics. I think that if I get the chance along the way, I want to. If I get the chance along the way, I think I want to restrict to things that are relevant, so have Q of X as a special one. Feelsley in chat asks how long the stream's going to be today. I'm live all day, so 9 till 5. The joke is that it's replacing my normal job for a week. So I'm just going to keep going. It's possible that this VOD gets put on YouTube at some point, in which case you can see from the runtime of this video how long I actually stayed alive. I'm doing a lunch break at some point. Do streams normally have lunch breaks? Twitch help wasn't very helpful here. Like, do streams do lunch breaks? Is it like cricket? Right, okay, we've got a Quintic fact, but I think it's time to go back and look at rings, so that we can get to grips with what those are. Okay, quick look at the map. So we saw the Quintic, we saw the mountain. It's like the end of the first Hobbit movie where they see the mountain. I think, oh gosh, that mountain's a long way away. We've seen the Quintic. There are some things in there about irreducibles and, oh my goodness. We've got to cross this mountain range of understanding those rings to get in there, which I think is where we're going next. My plan for this is really to just sort of show you what it's like to study maths. If you're a maths student at university, then you spend a lot of time looking at lecture notes trying to work out what's going on. So I've also got these rings notes from Richard L, which I picked off the Oxford Maths website. If you want a link, they're on my homepage, which you can get to via a link on my Twitch page. So I know that's complicated. I couldn't work out how to do a Twitch. I couldn't work out how to make that linked. Anyway, never mind. Here's the syllabus for the Rings and Modules course, which is exciting to me because, look, it's going to explain polynomial rings, which we're excited by because those are the things we're trying to understand, I think. Polynomials are just the theme for this week. Fields of fractions, characterization, good, okay. I saw a homomorphism in the Quintic, that page of Quintic stuff. Quotient rings, ideals, okay. Isomorphisms, Chinese remainder theorem. Oh my goodness, ideals, so now these things are linking together. Examples of ideals, always love examples. Constructing fields, we do need fields. More examples, including complex numbers, hooray. Degree of a field extension is going to be important because field extensions are important. I think somehow adding in these radicals, adding in these square roots and cube roots is I think some sort of field extension, so we're going to learn about those this week. We've got a whole bunch of these. This is essentially the one thing that I remember from doing this course, or this sort of course as an undergraduate, all these different things that a ring could do, to be principal ideal or to be Euclidean, and some of those imply each other, which is not a great takeaway because it's just a load of, look here, it's just a bunch of acronyms. And there's Eisenstein's criterion, which we saw on the Quintic page, so this is exciting. Modules, my hot take is that we maybe don't need modules for this week. So, although this material is really cool, really good structure of finitely generated abelian groups in particular, I think it's not relevant to our quest this week. Prepare to be wrong. Field is off back after college. Aha! You see, there you go. I do this. I did this for so long today. Cool. Right. Okay. So excited by rings. Probably want this kind of factorization thing. Probably want Eisenstein's criterion. Tough life. I think we should just get going. Let's learn some maths. That was supposed to be really cool, and then it didn't quite transition at the right moment. Notation then, okay, great. And here's a big list of examples of rings. This looks fantastic. I think I want a copy of this separately. Yeah, I want a copy of this. I'm not sure about that. Okay. So what have we got? Right, okay, I'm going to jump between this and my notes to try and get some of this down. There's a lot of letters here. How many of these do I want? I like this one. So obviously I want integers. Right, okay, notes. So integers are things you remember. Whole numbers. So these are really good because you can add and multiply them. But you can also do that on these other systems as well. So modulo n, these are integers, but you throw away multiples of n. So, for example, it's like looking at Z10 would be like looking at the last digit of numbers. So in Z10, there are only 10 objects, 0 up to 9, and the rules for addition and multiplication are, if you like, do your operation, but then only return the last digit. So you see, if you've only got 10 objects to play with, you need to define addition to be one of those 10 objects. And multiplication works in a pretty similar way. You take the last digit. That said, 10, of course the last digit thing is all about base 10, because we've got 10 fingers or whatever, 10 digits, which is a little bit circular, but hey, you could do mod other numbers, looking at the last digit. The reason that's nice is because it obeys multiplication and addition. Okay. Quaternions, I can't remember how they work. Hopefully it's explained in this course, if we need them. I've heard they're good for solutions of something. I think they're not associative. No, that's the next one. I think they're not commutative. I'm considering restricting myself to commutative rings, ones where multiplication commutes. You can do it in either order, because the polynomial rings that I'm interested in for a commutative ring are themselves commutative. So maybe I can get away with only doing commutative rings this week. Okay, I've decided this list is not entirely helpful yet unless we start learning about rings. So let's go. I just got to recap because I think this course is a second year Oxford course, after the students have learnt rings in the first year, but luckily, like 8-0 linear algebra, but luckily they've got the definition here again. Definitions play an important role in mathematics, and they let us understand what something really is. And anything that obeys this definition is one of these, anything that doesn't is not. And if we want to prove anything about these, then we need to use the definition. That's where we start. To prove that a ring is something would be to prove that everything that does this does something else. That was quite vague. Right, okay. Rings essentially say you can add and you can multiply and you get back something in the ring. They're associative, commutative. The associative is fine, we don't need to worry about brackets. There's a 0, which is sometimes written 0 subscript r. There are inverses for addition, but then in multiplication world, multiplication and division, no, hang on, that's not division, that's distributivity, isn't it? You can, so you can multiply, and that's fine, you don't need to worry about brackets, but the distributive law says that multiplication and addition work together nicely. These are good. Okay, so, and I've sped through that because I already knew what a ring was. If you just learn what a ring was, the takeaway is that you can add and multiply, but not necessarily divide. So things to think about are the rings that we were just talking about, so integers or integers modulo n, where you can add integers and multiply them. You can't necessarily divide by integers. I mean, I know you can in your real life, but 3 divided by 2 is not an integer. So there isn't an integer in there that would be the inverse of 2. Okay. Right, commutative. If multiplication is commutative, the ring has identity. If I sort of think there should be an identity, but never mind. All the rings that I'm interested in have got an multiplicative identity, I think. Avoiding collapse, that one's interesting. So it says that 1 shouldn't be the same thing as 0. Okay. So basic rules of algebra. What have we got? And these are left as exercises, which is a classic thing for maths lectures. You can add, so this one's true, whoops. This one's true because if a plus b is a plus c, then you could add negative a to both sides. These all look pretty obvious to me. Okay, fine. Right, most of, but not all of the rings we will study are commutative and also have an identity. I'm going to say CRI, which I saw on the list of examples. Oh look, here are some more. ZQRC, complex numbers. Commutative also have an identity. Good. Okay, so I like it when they say this sort of thing, that a ring is halfway between a group and a field. I mean, that's only helpful if you know what a group or a field is. Briefly, a group does a kind of one operation well, and a field does 2 operations really well, in some sense. The ring's halfway through, halfway between. Okay, what are we doing? We've got polynomial rings already. Here they are at the bottom of the page. So if you take any ring, this is already amazing. You take any ring, then we can make R of x the ring of polynomials with coefficients in R. And there's stuff going on all over the place in that sentence. Partly R of x the ring of polynomials with coefficients in R. So this is a ring. It is a ring because you can add things component by component. Here we are. Component by component. And you can multiply this rule for multiplying looks really complicated, but in fact it's just multiplication how you would want multiplication to work. Have we used the fact that it's commutative? No. Have we used the fact that it's an identity? No. So this is just true for all rings, so it's pretty good. So we can do sums and products. And then the thing that is really weird is that because that is itself a ring, you can define a ring, polynomial ring over several variables. Here they're called x1 to xn, but I think it's easier to see if you call them x, y, z or something. Let's just use x and y to start off with, right? They're defined inductively by, this is too complicated for me, sorry. So this says this. There's 2 sets of square brackets here, which is a bit surprising, perhaps. I think maybe I was expecting this to be defined somehow as the sums of different powers of x and y. But really what it's doing is to say r of x, those polynomials in x, that is itself a ring. So then if you bring in y as well, what you're doing is you're taking polynomials in x as the coefficients for y, which is just quite a weird way of thinking about polynomials in x and y. I guess it's true. I need an example, sorry. So something like this is a polynomial in x and y. It's something that I would expect to find in this ring of polynomials in two variables. I guess what we're imagining is that this is the coefficient of y, this is the coefficient of y squared, and there's a coefficient of 1 here for the coefficient of y cubed. Each of those coefficients is a polynomial in x. I hope that we just write these as this, and that the definition doesn't really matter. In particular, I suppose if we're being a real stickler, it's not obvious that these are the same thing. Y and x and y. I suppose maybe they're not supposed to be the same thing. I think they're going to turn out to be isomorphic, which is a word for basically the same shape, the same sort of properties. It would be really odd if they weren't extremely similar objects. Right, and we've got a reminder here that degree doesn't necessarily work the way you think it does, and that's because your rings might have things that add up to 0, which is a weird thing to think about, of adding up things and getting 0, but it can happen because in a ring like Z4 we've got this happens. Oh, we've squared something. I think I want my own example here. Use this one instead. What have I got? There's bars on here. I'm going to put bars on mine as well. I think I want my own example. So it's I guess they're bars because these are to represent the idea that these are. I put a bar on my x. That's not right. These are sort of conjugacy classes, I guess. Yeah, that's not the number 3. That's the element things congruent to 3 in Z4. I think there should probably be some bars over here as well. There's bars on the ones on the right. I guess 1 is the identity. So, yeah, hang on. So I think I need to understand Z4 a little bit more. Sorry. So there's 1 bar, 2 bar, 3 bar, and 4 bar, which I'm probably going to call 1, 2, 3, and 4. Maybe that's actually more normal to write as 0 bar. I suppose 0 bar is equal to 4 bar or something. And then the rules for addition are almost what you think. It loops around. So 3 bar plus 1 bar is 0 bar. 3 bar multiplied by 0 bar is 0 bar. Okay. The only weird one maybe is 3 bar times 2 bar, which is 6 bar, which is equal to 2 bar. Modular arithmetic. Is it always like this? Yes. Good. And here's a fact about Z8. Quadratic x squared minus 1 bar. It's got 4 roots. There are 4 different things that square to 1 in Z8. 2 distinct factorizations. I think these rings are... so these modular arithmetic ones seem weird in that they've got an odd number of solutions to quadratics and distinct factorizations, which worries me quite a lot. I'm hoping that we don't need those for the Quintic quest. It's sort of an interesting warning, but I'm hoping that if I'm just interested in things like Z and Q, that I don't need these. Let's go on, and I'm going to accelerate a little bit. What else have we got? Let's try and look at... Yeah, maybe that's my aim, to try and look at all the pages that we need to understand, to map out what we're doing. You can put matrices in your polynomials. Direct sum means you can take pairs like coordinates, which makes me think about vectors, I guess. Yeah, these things look like vectors in example 13. We've got continuous functions, which sounds really complicated. Yeah, okay. Sure, I believe it. So continuous functions. This sounds like to engage with this, I need to remember a lot about continuous functions as well. Pointwise addition and multiplication. Oh gosh, okay. So then there's a zero function. Anyway, even numbers has no identity. Oh, what? Okay. So how do these work? The even integers form a ring under addition and multiplication, because when you add two even numbers together, you get an even number, and when you multiply them, you get an even number, so it's closed. I guess associative because it's just numbers. It's commutative, yeah, sure. Has no identity. There's nothing you can add to 2. No multiplicative identity. There's nothing you can multiply 2 by to get 2 in the even integers, because 1 is an odd number. It's funny how understanding it takes you to some odd places, because 1 is odd. Okay, good. So that's a ring with no identity. Hopefully I don't care too much about those. Right, okay. End V. Maps? Endomorphisms, I think? These are maps from V to V. Zero and identity. What does that mean? The zero map. V is a vector space, okay. Vector space. The dwarves. If you take things from the linear... No, these are linear maps. Oh gosh. So this is linear algebra as an example. Gosh. See what I can remember. So you've got a vector space, and then a linear map is one that respects addition, right? You can form a ring. Okay, fine. If you do one of those and then another, oh gosh. So addition and multiplication means... Oh no, sorry, it's not function composition for the combination. It's to take something like... So you've got your x in V as your member of that vector space, and you've got two linear maps. Then this thing means to... this is defined. You could add them together in that image, which is also V. You could add together the images of f and g and call that the image of f plus g. So you can construct this new map f plus g, which is just apply each function and add them together. Fine, okay. Power set p of x. Okay, right, okay. Let's not think about power sets right now. There's all set theory going on here, so I'm fine. Okay, there are diverse examples of what a ring might be. Good. Sequence spaces, do I want these? Not so much. Gaussian integers I love a lot. These are complex numbers. This is a great example, I think. So A and B are whole numbers. So the kind of mental image is that these form a kind of grid. 1, 2, 3, I, 2i, 3i, 1 plus I, 2 plus I, 3 plus I, 1 plus 2i, 2 plus 2, but what am I doing? You could be negative numbers instead as well. So the grid extends this way too, and this way, and this way. And it's got a bit wobbly up here, but there we go. Oh, a weird distortion that's making my eyes go funny. A kind of grid of complex integers, Gaussian integers after Gauss. You can add them, you can multiply them. Have we got an identity? Yes, it's the number 1. Identity. That's the... I've got to remember that identity seems to always mean multiplicative identity. The additive identity is the kind of 0, which you've got to have. you've got to have a 0. It seems a little bit optional whether your ring has an identity or not. I kind of always want an identity, I think. In both senses, a 0 and a 1 that are different. So those Gaussian integers are important because complex numbers are great, but they're an example of taking the integers or taking some sort of real numbers and then adding in a new element, I. The way they've been written there looks a bit like polynomials that you plug I into, right? So we already had this polynomials, and now we see this notation for Gaussian integers. I guess that sort of works, because if you took a polynomial, let's be more original with my polynomial, please, and you plug in I, then you get something that is a Gaussian integer. There's different representations though, because this is going to be the number -6 minus 2i, which I would also get if I plugged in I to the polynomial -6 minus 2x or something. So there's different polynomials that are going to evaluate to the same Gaussian integer when I plug in I. But it feels like they might be related. So the difference between those might be something nice. Yeah, possibly. What's the difference between those? There's a 7, there's 4x. Yeah, 7x squared and 4x cubed. So the difference is a multiple of 1 plus x squared. So these things are kind of the same if you believe that x squared plus 1, if you ignore multiples of x squared plus 1. And because the difference between them is 7 plus 4x plus 7x squared plus 4x cubed, which is 1 plus x squared times 7 plus 4x. So if you believe that 1 plus x squared is the same thing as 0, then those things are kind of equivalent. That's just like modular arithmetic again, but instead of calling a number the thing that I ignore, I'm calling a polynomial one of these elements of z of x. We're going to see later on that that process of quotienting, of saying, these things don't count, is how you get from something like this to something like that, by adding in the number, which is sort of like plugging in the number I, but also not really. Plugging in the number I is a many to one function. How many is something that we might like to understand. What sort of stuff do you have left over? Right, cool. I've realised that at the moment I'm talking as if I know what's going on, which is good, and I should probably try and get to the bit where I don't know what's going on, because that's a little bit more authentic. Is there a bit at the start of The Lord of the Rings where everything's going well? Yeah, there's a bit at the start where everything's going well. Yeah, and then it goes badly. Yeah. Goes really badly. Right, good. Quaternions. Speaking of things going really badly, here's quaternions. Oh my goodness, where do these come from? They add bright K. They look like vectors if you call them bold I, bold J, bold K. Anyway, never mind. Those rules are a bit odd, aren't they? IJ's K minus, oh my goodness. Right, okay, so you could take this rule and multiply both sides by K to get, and then that's -1 to get IJ is K. Oh great, okay. So you can play games with these to get from one point to another. So H is not commutative. Is there a multiplicative identity? Yes, there's number 1. Oh my goodness, those elements form a group. Are those the elements? Oh no, because you could have numbers in here. And there's a group. So these things behave nicely under multiplication. Nicely enough, I suppose. Yeah, that's a bit odd. So if you've got a ring, they're calling out here, this is a bit odd, they're calling out here that some of the elements form a group. But that doesn't feel that surprising. Oh, okay. So in a ring, you can multiply but not necessarily divide. Not everything has an inverse. I guess what they're saying here is that all of these elements, choose these particular elements, they've got inverses. Do the other ones have inverses as well? Is this a field? So a field would be if everything's got an inverse, except 0. I think it's probably true. Not obvious from the definitions, right? Yeah, I think it's true though. Right, okay, we've got subrings next. Good, seems to be, I think, what you want it to be, things within that ring. It's a ring inside a ring. If you're an S, then you can add and stay in S, multiply and stay in S. Yep, good, okay. So your integer coefficient polynomials live inside your rational coefficient polynomials. 2z is a subring of z. It's not as good, is it? I don't know, this seems important. Modular arithmetic doesn't live inside z. That's tough, isn't it? Because Zn really feels like it has the numbers 0, 1, 2, 3 for Z4, for example. Really feels like it has the numbers 0, 1, 2, 3. It really feels like a subset of Z. Doesn't count. I suppose the addition is totally different. That if you believed that 0, 1, 2 and 3, the numbers in modular arithmetic, actually lived inside Z, then when you add them you get different things in those two places, so that would be weird. If you add them you get 5 in Z. If you add 3 and 2 you get 5 in Z, but if you don't get 5 in Z4, so sort of squaring that circle would be tricky. And I guess it's why they've been labelling them with bars on the top, because they represent equivalence classes, things that are equivalent to each other rather than elements. That is tough. I think when you learn about modular arithmetic the first time, it's really, here are some whole numbers and some different rules, rather than here are some objects that look a bit like whole numbers. Maybe it'd be good for us if we learnt modular arithmetic as, here are some sort of colour codings, like colour in the whole numbers red, yellow, green and blue, and there are some rules for combining together red, yellow, green and blue when you add or multiply those colours together. But the colours are not actually numbers. They don't behave like numbers from Z, and they're definitely not elements of Z. Now I'm wondering, are the even numbers definitely a subset of numbers? I suppose, yeah, this is stupid, but now I'm worried. Good, okay, we're half an hour in, and I've got myself worried about what even numbers are. Clip that. Oh no, that's actually a thing now, isn't it? I actually could clip that. Let's not worry about that. Okay, here we go. We're going to jump in with some definitions next. Element is a zero divisor if you can multiply it and get 0. Not 0, B and C. In a commutative ring, fine, okay. Just if there's something that you can multiply it by to get 0. And an integral domain. Why is that called integral? Sort of entire, right? Rather than integration. I'm supposed to think about like an entire object. No zero divisors. Okay, so never have x, y equals 0. That seems like an easier way to remember it to me. So integral domain, I'm going to abbreviate to ID. Yeah, okay. So is that true for some of the rings we've seen before? For integers, yes. For rings, for sort of modular arithmetic, it's interesting, isn't it? Because in Z4, you've got things like 2 bar times 2 bar is 4 bar, which is 0 bar, which is 0. So you can multiply things together and get 0. Okay. So sometimes rings are not integral domains. Sometimes they are. Okay. Right, units defined down here. Is there a b such that you can multiply it and get the identity? And again, if we're commutative, I'm not going to worry about all of the distinction between AB and BA. So how am I going to write this? Units have inverses. I find it helpful to try and summarise the things. So that I've got a kind of short phrase for remembering what something is. Anyway, here are some examples. Z, Q, R and C are integral domains. Fine, okay, if you multiply two fractions together you never get 0, two real numbers you never get 0, two complex numbers you never get 0, unless one of them is 0. Terms and conditions on my short form way of saying things. Okay, so this is the polynomials over here which I'm interested in. That's an integral domain because it's got a concept of degree, right? So if you multiply together two polynomials, you're not going to get the 0 polynomial because it's going to have a higher degree, or some non-zero degree, unless one of them had 0 degree. Both of them? No, yeah, so degree multiplies. Degree is multiplicative, and in Z, it's fine. So if you want that to be 0, then one of those has to be 0. Is R of X with, instead of reals, just this? No, we already saw, right? You could do something like, what's if R is not an ID, not an integral domain, then there are just like constant numbers in there, like 2 bar times 2 bar, rubbish. If R is an integral domain, is R of X an integral domain? That seems like a good question. Is it on this page? If R is an ID, is polynomial ring? Okay, let's write it down here. If R is an ID, so this is just some general ring, is R of X polynomials over that ring an ID? Seems like the sort of question we should ask ourselves, right? Sometimes when studying maths, you need to ask yourself a question. Usually they hand out question sheets as well of suggestions for questions, but sometimes it's good to test your own understanding. I'm now going to try and think about that question. Here we go. So, R is an integral domain. What do I think? So I think this idea of degree possibly extends so that so let's think about this. So the top coefficients, if I have sort of an x to the n and bm x to the m, then when I multiply them, I'll get an bm x to the n plus m as kind of degree. But an bm is not 0 because these things are not 0, and R is an ID. R is an integral domain, so that means that this coefficient is not 0, great news. That means that my polynomial that I got from multiplying is not the 0 polynomial. I need to tidy that up a little bit. If I was writing that up as a proof, I would put in a lot more words, right? So it'd be something like let f of x and g of x be non-zero polynomials. Dot dot dot. Right, good, okay. Vaguely powerful, right? If R is an integral domain, then so is R of x. So you could continue that process, because then R of x and y would also be an integral domain. In particular, Q is an integral domain, so Q of x, if we care. Let's write that down. And do I want Q of x and y? Well, maybe not. Okay. Yeah, maybe this should have been one I checked anyway, because I care about that polynomial ring quite a lot. If you've got two polynomials with rational coefficients and you multiply them together, you don't get the 0 polynomial. Sounds really obvious. My proof of that is look at the top coefficient. It won't cancel, promise, because those top coefficients are rationals that cannot multiply to give you 0, because Q is an integral domain. So when you multiply them, we're good. Right, is this on the board? Feels like it should be on this page somewhere. No? Cool, okay. So if R is an integral domain, then you can kind of divide. This is very exciting. Even though there might not be an A inverse. So the point of this is, if this was like a field or something where you could just divide by A, that would be good, because you could just multiply by A inverse and it would just be true. But we can get away with not necessarily having an A inverse. Guess we should try this on a case where there's no A inverse. Oh yeah, sure. So like Z, right? If 2 times... What am I doing? I'm about to write down something really stupid. 2 times... yeah, okay. If 2 times x equals 2 times y... This is terrible handwriting. Okay, if 2 times A equals 2 times B in Z, then A equals B, which is really, really stupid, sorry. And there are 2 ways to prove that. Stupid fact. One is to just divide by 2, but hey, what are you doing dividing by 2? You're multiplying by 1/2 a number which doesn't exist in Z. You've got this kind of advanced idea about fractions, right? But in Z, there's no such thing as a half. But this other proof that we've got here is that you can rearrange it to be 2 times A minus B. Use the fact that Z is an integral domain. You can never multiply and just get together to get 0. Which means that A minus B must be 0. It's kind of cool. I've used different letters in my example to the ones on the page. Does that somehow hint that fractions exist, right? That you can kind of get away with. The reason you might want inverses is so that you can cancel things like that, I suppose, and also solve AB equals just C. Inverses are good. Okay, I got distracted. What are we doing? Oh, it's just, we've missed some notation. R star is the set of units in R. That's a group that's just well behaved. Units are nice. They have inverses. So units have inverses. Was that my short phrase? What's my short phrase? Units have inverses. Good, okay. I should maybe collect these together. Let's do a quick quest log. So back to the map. What have we learned? we've learned that you can't have x times y equals 0 in an integral domain unless x equals 0 or y equals 0. We've learned that units have inverses. And we've seen a whole bunch of notation. Not bad for a first hour. We've picked up some ideas about what rings are and some ideas about things that rings do. We had a viewer for a bit. It's been a successful live stream. Yeah, this is what life is like. Back in. We're still very much in my comfort zone, really, which is good. I thought we'd get out of my comfort zone much faster, but I'm still happy. Haven't been attacked by Nazgul yet. Right, here we go. Oh, I can't remember what all of these are. Something about matrices. The sort of units of your ring of matrices are like general linear. The ones with determinant 1 or something. Oh no, ones you can invert? Yeah, ones you can invert are the units. You've got to remember the ones that you can invert. Isomorphic, fine. Okay, there's a group facts at the top for recognising the units are well behaved. They form something called a group, which I'm hoping is not too important. Okay, an element cannot be both a zero divisor and a unit. I'm kind of hoping there aren't any zero divisors in most of the things that I'm interested in. There is finite commutative. Yep, okay. Finite, interesting. Constraint. It's one-to-one, blah, 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 blah. Right, okay. We've got a field now. Oh yes, we've got a field. And it's revision for the second year Oxford students, I think. So it kind of goes ring. Group is somewhere down here for just having one operation. Ring is somewhere between group. It's a bit better. It's got a second operation that's almost there. Integral domain is a little bit better than a ring because you don't have any zero divisors. And then field is even better because everything's a unit. So kind of like that evolution between groups and fields. So nice things like Q are fields. Rubbish things like Z. What do I want to put down here? I don't know, things where you can't add, right? Things where you can only multiply. Like, that's not how you write Q8. Messy things down here. Where it's nice rings, like. Good, okay, I should probably put more examples on this. Maybe a less stupid example of a group. So down here for my group, maybe I should have something. No, I kind of want a weird one, right? Like, say, some weird group stuff, which has like a single rule about how you operate to binary operation. Rings, and then integral domains where you've got no zero divisors. Wait, hang on, is F5 actually a field? Yeah, it's actually a field, isn't it? Sorry, what's going to be my example of an integral domain that's not a field? Oops. Z? Z. Integers are an integral domain because you can't get 0 when you multiply them, but it's not a field because you can't divide. Good. Okay. So field down there, every non-zero element is a unit. We fit 10 o'clock. I can do this. This is just a normal kind of thing to do, isn't it? It's just how life works. Whoa. What's down here? Finite integral domain is a field. Oh my goodness, that sounds quite big. So those concepts are quite close together, integral domain and field, in some sense. If you're finite, then whoa, you can get one from one to the other. R be a finite. Oh my goodness. I love this sort of proof. Consider the map given by multiplication by just anything. A is anything. By the cancellation law. The thing that was almost there, right? So it's almost there to say you can kind of, that cancellation law almost lets you divide. I think it's 1 to 1. What does that mean? Wait, no, I know what 1 to 1 is for each of these, one of those. Oh, right, no. Cancellation law says that you can never have two things like this. So it says that this is injective. But because R's finite, if you've got an injective map from R to R, it's also surjective. So it's bijective. So particular, there is an R such that you can multiply A by R and get 1R. So it's kind of a pigeonhole principle in a way, I think. Show me an element that you would like the inverse for. Find me the inverse. Multiply it by absolutely everything. All 28 members of your ring or whatever. Multiply it by absolutely everything. You never see the same thing twice, so you're going to see the identity at some point. Weirdly, that's not true for infinite rings, because for infinite sets, you could do something like have the integers get sent to the even integers, which can be 1 to 1, but not onto. It'd be gaps. Loads of space in an infinite set. What are we doing down here? Field of 4 elements. I don't like the way that people start saying the straight away. It turns out that I think these things are all isomorphic. There's a unique one for each. There's a unique one for each order. But here it's a finite field, and then it becomes the finite field, which is not proved yet. You shouldn't just start saying the without proving that's the only one. Anyway, this is the only one of order 4. Finite fields are a bit weird. They're going to be important, so I should stare at this a little bit more. Right, okay. So, yeah, okay, there's not very many possibilities about what you could do for multiplication. Whereas we've been doing an hour and we're on page 8, which reminds me of something I heard about filming Harry Potter once. When they were filming Harry Potter, they got through about 1 page a day or something of filming the script. So they just, oh my goodness, can you imagine? A whole day for a page. I'm going to speed up a little bit. So the concept of characteristic, which I quite like. I don't love this notation for multiply it by an integer n, which I guess means r plus r plus r plus r plus r n times. In general, I don't know how you can't just multiply by some sort of alien element that's not in your ring. Multiplying by an integer is kind of defined, because you can just add things together. Multiplication and addition don't have to have anything to do with each other. In polynomials, multiplication, I guess, kind of does mean repeated addition if you multiply by an integer. It always does. But you got multiplication by a different polynomial doesn't necessarily mean anything to do with adding. So we can't just do that. I think the ones that are more interesting to me are the ones where no such n exists. So things like z. they're defined to have characteristic 0. I guess the thing to imagine is like you go off on this walk, so you start at 0, and then you add 1, because in your ring with identity, what's R? And for all R in R, excuse me, in particular for the identity, let's think about the identity. You go off on your walk like this, and maybe you get back. Maybe you get back, in which case, fine. You've got a loop like this, or a ring, perhaps. Or maybe you don't get back. Maybe you're like the integers and you just keep going. There's now an attempt to draw the number line. So that's characteristic, I guess. I'm trying to understand this where it says for all R. Is it okay to just check the identity? I want to just check what happens with 1. Let's see. So if it's true for all R in R, that nr is 0, then it's definitely true that n times the identity is 0, because that's an example of some R in R. And what I'm just hoping this is true, right? If n times 1r is 0, then I think I can multiply that by just any r. So that's, I think it's enough to just check the identity. Oh, in the event that R has an identity. I'm an idiot, it's written right here. That's going to happen a lot. If it has an identity, you can just check what's going on with the identity. Good. All the fields I care about can have an identity, so I'm just going to check the identity. If it doesn't have an identity, say 2z doesn't have an identity, but you could still say it has characteristic 0, because if you keep adding numbers together, you never go back to 0. Have you got a weird ring, like something where like 2 different circles, like 2 and a 3. So that one goes round every 2, that one goes round every 3. Can I try and build something where the characteristic is 6, because you've got to go around 6 times? Now we go on a little adventure to do like... So I think that might just be isomorphic to z6 anyway, but this includes things like this. Hang on, that is the multiplicative identity. When you cross these Zn groups together, do you always get something isomorphic to some other set group? I suppose you probably do. Good. All of these things have got 0 characteristic. F4 has characteristic 2, the field with 4 elements. Now I regret not having a model for F4. I want to go back and look at F4 quickly. There's F4. So, oh yeah, okay, so here. Field of 4 has got an identity, because it's got inverses and everything. If you have 1 plus 1, you get 0 in the field of 4 elements. So it's a field of characteristic 2. Fine, okay. Ring R of 4 elements with the ring working like, this means isomorphic to C4. Multiplication defined by what? What? I love this. That's mad. This is very much not an integral domain. This sort of says build a ring. Excuse me. Build a ring by taking any group for your addition and defining multiplication to be absolutely ridiculous. Multiplication absolutely ridiculous to always give you 0. Huh. So if R is an integral domain, and the characteristic is prime or 0, and then let's talk about the identity. Do integral domains always have an identity? Oh yeah, okay. It's talking about the identity, but then these things factorize. And look, here's all the one adding. Okay, cool. More mapping. Fields can contain. Okay. Fields containing other fields. Subfield. Fine. Okay. These things can live inside other fields. Oh my goodness! Look at this. The smallest subfield of f is the one generated by 1f. So subfield would need to contain 1f, and then you could just keep adding it, right? And you'd get a subfield because it might loop round or it might go off to infinity. Those are the two cases. Fine, okay. Ooh. So phi from Q. This looks fun. Oh, but it's just because you can define both of these things on the right. If you define these things on the right, then you can have an image. Field of fractions. Sounds important. It's where I keep my fractions. It's an equivalence relation like this, which looks mad. And then it looks even worse underneath. But these things are less surprising if you realise that they're basically just fractions in disguise. These fractions are equal if kind of m divided by n is equal to big M divided by big N. So it's considered equivalent on those. And weird addition and multiplication. So is this sort of like taking integral domain, which kind of almost has inverses, and then just hard defining the inverses, right? As your inverses should look like fractions, really. So take your ID and just, come on, let's divide. Seems like kind of the attitude, I think. Being an integral domain is really close to being a field. You should just define all your fractions, including inverses and division, right? Huh, okay, so integral domain is really close to being fields. So much so that you could do this. This looks important. I'm not going to read it now, but it looks important. Q is the field of fractions of Z, that's good. Right, okay, you got to check a whole bunch of stuff. Extending inclusion. Okay, so that last bit looks really clever and technical. Okay, here we go. No, these all look quite sensible examples at the bottom there. Field of fractions of Z of pi. Wait, does that mean like... Oh, because you can kind of pull out the factor of pi, right? Pull out the factor of pi to get like anything. Yeah, I want square brackets here, by the way. To get like a, so this is 1 plus 3 over 2 plus pi. Wait, that didn't help me. That doesn't look like an element of q of pi to me. What am I doing wrong? Oh, field of fractions. No. What am I doing wrong? What am I doing wrong? Maybe it does mean round brackets. There's twice in here, right? Why are there round brackets on that q of x? Okay, I thought these examples were straightforward, but I don't understand them anymore. Q be fractions times pi, right? This would be fractions times pi, like a over b plus c over d pi. That is not what I have over there. 2 seconds. Okay, I don't understand this one. What have we got coming up? Okay, that's section 1. Woo! More ring stuff that I'd like to understand. Principal ideals, oh my goodness. Okay, what's an ideal? Some sort of fancy subset, right? Whenever these things are together, it's closed under addition and multiplication. Oh no, multiplication by r in the ring. So ideals, you can multiply them by anything. Huh. Any text which insists that rings have identities will then have a convention that ideals are not generally subrings. In particular, ideals are... Oh, so your ideal might not contain the identity? Yeah, your multiplicative identity might or might not be in there. Interesting. Right, so if you insist that rings have ones, then your ideals might not be subrings because they might not have ones. Whereas in this text, ideals are subrings because subrings don't have to have ones. This stuff about multiplicative identities seems to be a bit of a distraction, right? The smallest ideal to contain A, so it's got A in it, and then you're going to have to put in everything else. Why they multiply it on the left and the right? Oh, because it might not be commutative. Is this ideal a principal ideal? Can you generate it with one element? Okay. I think we've got some examples with function spaces down here. S is a subring but not an ideal. Okay, fine. You can generate ideals with lots of things. Good. Skipping ahead a bit. Right, okay. For reasonable algebra, some good phrases in here. You can define cosets where you add things on and they have some operations to form the quotient ring. So this is the idea of taking a ring and then considering everything in an ideal to be cosets. So like before, in this ring, there's an ideal generated by x squared plus 1, which means that's a principal ideal, means takes x squared plus 1 and multiples of that. So multiply by any p of x, I guess, any polynomial. That's quite natural for thinking about like factorising or thinking about pulling out a factor. Like the factor theorems, giving you vibes of all of that sort of stuff from A level or equivalent. And then the quotient ring is this idea, aha, what if we ignore factors like that? What if we just consider all of these things to be basically the same, right? Or is it adding, oops. Yeah, if we consider if we consider all of those things, if we consider all of those things to be like being 0, which would happen if we plugged in the number I, which would give 0 over here. But we don't need to think about the number I. We could just insist that all these things are to be considered as if they're basically 0. And then you've got this ring, so the notation is like this: ring quotient ideal means look at this ring, but consider everything from that ideal, multiples of x squared plus 1, to be essentially 0. And you've still got some stuff left, because you've got things like, well, before we saw minus 2 minus 6i is kind of an element. I guess we now mean bar, like for modular arithmetic, we kind of mean that equivalence class of that element plus multiples of x squared plus 1 is in that example of our quotient I. Okay, this is good because, did I mean that? Do I mean x down here? I mean x down here. The arithmetic on these things, the arithmetic on that quotient ring, the arithmetic on that quotient ring turns out to be exactly like z of I. We're going to see that in a bit, I think. Still going well. Still going well. Oh my goodness, look at all these things to check. Okay, here's a good one down here, 58. R is q of x, and try and factor out x squared. The thing you get is not an integral domain, because in there's x bar, which is the notation for things that are equivalent to x in this new world. But if you multiply by itself, you get 0. Excuse me. So here's the ring. If you consider x squared, p of x, all of those to be essentially 0, then these things, that's supposed to be an f, right? These things is an example of something that's in the quotient ring? No. So I'd write that as an example of something that, when you quotient, gives you this is in this quotient set. Quotienting is that operation of considering things to be equal. Every coset in R mod I uniquely represented as this, but hang on, now you're not writing bars on these. I want to write a bar on the whole thing. I guess there's algebra on these things that you could... Oh, I don't love it. I was kind of like doing algebra on the cosets using Q, because Q is our element, that's our ring that we're using for the coefficients of a polynomial up here. So we could always say that these things A and B just behave as operations on the quotient thing, like this. Like I'm splitting it apart. Bar here has got nothing to do with complex conjugation, which is going to be irritating later on, I think. Sort of, I want to not worry about this too much. Let's get some 0 divisors. Okay. So these ones, one we're quotienting in this case Z2, which I don't want to think about too much. It's sort of slightly weird ideas about what these things are. So Z2 doesn't contain that many polynomials because, well, there's not that many things in Z2, right? There's these. I think this might be it for elements. Oh no, so we can keep going. Oh yeah, okay, fine. X squared plus all of those things. X squared plus 0. And keep going. But if you consider x squared to be, if you consider that to be 0, then you get these 4 things. It's your quotient sets. And now they're writing 1 bar. Okay, interesting. Let's just hope it never matters too much. See, I think you could consider this to be x bar plus 1 if you allow yourself to do algebra using Z2 on the coset pairs. Just maybe you shouldn't do that. Maybe you just shouldn't do that sort of algebra on the cosets, because the cosets have algebra with themselves, but not really with Q. Yeah, there's kind of there's an action of Q on that set of cosets, but okay. Anyway, it turns out these things are isomorphic, they're the same. Oh my goodness, yeah, check all the operations. Yeah, we're not doing that now. Ring homomorphisms, these sound important, are maps that preserve addition or work nicely with addition and multiplication. Hello, now we're using star multiplication. I guess we've got 2 sorts in our 2 rings. It could be an isomorphism if that's bijective, so for each of these is one of those. Right, okay, these things behave relatively nicely. Fine. Okay. I remember seeing isomorphism right at the end on the Quintic page, but I think at the moment, fine, preserves. Okay, let's write this somewhere. Ring homomorphism. It's not really preserves because it's a different. Preserves would be if it keeps it the same. So let's put respect and times, and that feels like it goes on my quote sheet of things to remember. Preserves. Oh no, not preserves. We agreed respects. Okay, what are we doing? Down here somewhere. Yep. Okay. The map given by, oh my goodness. That's sort of p of x because give me a polynomial and return p of a for some a and r. Fine. Okay, this is a function evaluation. That's a homomorphism. Oh, okay, so this is going to help me prove that... no, this is not going to help me prove that you can plug in I to prove that things are equal to each other, because I is not a member of Z. I was sort of hoping that this would get me from things like, in the back of my head, I've got this like stuff about Z quotiented by x squared plus 1, I've got like Z of I, which looks a lot like plugging in I into the polynomial, but that's not what's going on here at all. None of that is what's going on here right now. Okay. Good. Oh, here we go. Here's a map from Z to Zn. So we saw earlier that those are not the same thing, but you can go from X to X bar. Brilliant. So many bars this morning. Bad start to a Monday, really. So it respects addition and multiplication. Okay, fine. Did I put addition and multiplication in my notes? Double check. Yep, both. Good. Okay. And then the only ring homomorphism going the other way is the zero map. Because, what's this say? You're supposed to get round to 0 again in Zn. Get back to 0. This doesn't seem super exciting right now. Yep, fine, okay. More examples of ring homomorphisms. R is not the same thing as C, that's pretty good. Because, yeah, you've got this element I which squares to -1. Those are different things. Good, okay, you can't respect multiplication. Kernel and an image. These are in bold. Must be important, right? Definitions are always important. Image works like this. It's things you can reach, and the kernel is the things that map to 0. Okay. And the kernel is an ideal, and the image is a subring. Fine, okay. The kernel is an ideal because whenever you... I mean, it's just at the bottom of this page. I should just read on, right? Rather than trying to think about it. No, thinking's good for me. Kernel is an ideal. I know it's on the screen, but I'm not going to look. Kernel is an ideal. That means we've got to check that. If you have I in your ideal, I in your kernel, and you have R in your ring, then we want to check that IR is in the kernel. Is IR in the kernel? And the thing we would check is that phi of IR, while homomorphisms respect multiplication, so that would be this, but this thing was in the kernel. So it's this, and 0 multiplied by anything is always 0. This operation happens in S, but fine, multiplication in S is nice. This is 0S, I suppose. So yes, IR in phi, in the kernel. Good. Definition of kernel up here. Definition of ideal hanging around in the middle somewhere. Definitions are important. Oof. Simulate. Good. Okay. The subring thing at the bottom there. Why is it not an ideal on the other side? I suppose our image could contain, well, so the S could contain all sorts of weird stuff that's nothing to do with phi or R or our map at all. Anyway. Kernel and image. Oh, function evaluation works like this. The kernel is, this is the factor theorem. Yeah, okay. The kernel of that evaluation map is any polynomial that's got a factor of x minus a. Huh, cool. So they can't do division algorithm, which is how you would try and do polynomial division, I think. But you can work with identities such as this. Now, what is that? It's a true fact, isn't it? It's a true fact by like multiplying out. So then what do? You take your so for the former means for the first thing, which is the kernel. So you take your general polynomial and you say, is this in the kernel? Well, let's suppose that it does give me 0. When I plug in, no. What am I supposed to do? I think I'm just supposed to evaluate it at A, right? Where was the definition of this thing? Down the bottom somewhere, wasn't it? I wrote function evaluation next to it. There it is. P of A, yeah, right, okay. Which just means plug in A. So if I plug in A, then but if I plug in A, then it just says that A to the n is equal to A to the n. What am I doing? What do I want? Okay, maybe I don't want to prove this right now. It's the factor theorem. For a general ring though, which is nice. General commutative ring with identity. Good, okay. Kernel image, yeah, fine, okay. Looks good. Where are we going? We've got more maps, more homomorphisms, more kernels. First isomorphism theory for rings, brilliant. We already did these. That was the notation for being an ideal, which I didn't ever write down. I should have. That's the subring notation. Fine, okay. And then this map from R quotiented by the kernel, which is exactly the sort of thing that I'm interested in, onto the image given by, take me something from this coset. So take like your element being minus 6 minus 2i plus and then plus 4x cubed with whatever it was. That's an element in the kernel, because when you what's my phi? Oh no. What's my phi? Whatever, the one where x squared plus 1 is the generates the ideal as the kernel. Okay. Return that number. Oh no, now I want the x. Ah! I'm jumping the gun a bit. General statement ring isomorphism theorem is, if you consider the things in the kernel to be basically 0, that's isomorphic to the image. The proof is kind of interesting, I suppose. It's sort of linear, right? Everything's just kind of nice. We've got this new map. So this new map phi bar, which is nothing to do with complex conjugation. It's just taking something from this quotient ring. Let's label that to the image given by, show me something in the quotient ring, and I will just take that representative thing. It's not actually obvious that this is like, I mean, it is a little bit fine, but that this is well defined. Because there's different representations of things in this element of the quotient ring. These things are only defined up to elements of the kernel, but then you get away with it because we're planning to apply phi, and it doesn't matter what I take from the kernel. When you apply phi, if you had something else from the kernel inside there, then when you apply phi, you get back to the same thing. Purely because the kernel is the thing where you apply phi and you get back. Okay. What are we doing? Oh, right, phew. Okay, it was well defined. The thing I just tried to say out loud. We got it in notes here if we ever need it. Good. Okay. Brilliant. So now, whenever you've got a homomorphism, whenever you've got an isomorphism. What am I saying? Let's read it once more. Whenever you've got a homomorphism, you can prove that two things are isomorphic. You can upgrade, provided you do a quotient. So down here, we had this quite boring example of a homomorphism where you take a polynomial and just plug in a, and that gives you your value in ring. These things are not isomorphic, it's a homomorphism. I mean, kind of the domain is much larger than the image, but if you quotient the domain, if you consider some things in the domain to be basically equal, then you get an isomorphism, which is that if you consider all polynomials with a factor of x minus a, ignore those, any polynomial with a factor of x minus a, well, that would be isomorphic to just the reals. Kind of by using this homomorphism and the isomorphism theorem, this looks quite powerful. It could tell us that some of these complicated objects where we're quotienting, could could maybe give us isomorphisms to simpler things. Whew. Ooh, okay. This is now getting good, I think. Because now we've got fun statements like this, which is what I've been trying to get closer to for a while now. So this is the map. It goes from real polynomials to complex numbers by show me your real polynomial and I'll plug in I everywhere. That's quite good. That's got some kernel. Anything with a factor of x squared plus 1 is going to be sent to 0 under this map. So it's in the kernel. I guess this set for all p, whatever. Kernel of phi. And in fact, anything, so that's the ideal generated by x squared plus 1. Principal ideal down here. If you quotient by that kernel, then you get the complex numbers. Is it obvious that's the entire kernel? Those are the only things. I suppose there's a definition of complex numbers in there somewhere to say that I is not the same thing as 0, but I squared is minus 1. Yeah, it's sort of not obvious. Maybe you, yeah, okay. Don't love it, I have to think a little bit. That's fair enough, I suppose. I mean, for example, it's also true that x to the 4 minus 1 is equal to 0 if I is 1. Yes. If x is equal to I, then x to the 4 minus 1 is 0. But somehow that's not... that's too high a degree. That's not the one we're looking for. I think it's this concept, vague memory of this as some sort of like minimal polynomial that we're supposed to look for, so that we can identify what that principal ideal actually is. I suppose along here somewhere, was the statement in this example is just that these things are isomorphic. I think there's some work to check that that really is the kernel. It really is generated by that polynomial, and not some other, maybe simpler polynomial. Okay. I suppose that polynomial is irreducible. Is that going to be relevant? We'll learn about ideals, I think, at some point this week. Okay. So plugging in root 2 is a good way to show that this thing is isomorphic to that. At which point you start to wonder, why didn't we plug in minus root 2, right? There are two numbers that make this 0. I suppose what we could show is that if you plug in p of x goes to p of minus root 2, which is a different map. Those things are different places, but it's kind of isomorphic. We would get something like this, but that's isomorphic to q of root 2. I kind of doubt that that's important, but still, I enjoyed writing it down. Okay, plugging in 1/2. Oh my goodness. Oh, and zx doesn't really have 1/2. It's kind of a bit cheeky, isn't it, to take a polynomial in z of x and plug in 1/2. But I guess this is defined as you've got your polynomial, z is in q, so everything's fine. Consider that as a polynomial in q of x. Kind of a bit. I guess nobody ever said that x was a number. When you set up your polynomial ring for coefficients of powers of x doesn't actually have to be anything at all. It's just some structure for your list of numbers. We're not doing anything with them, right? It's a function evaluation, as much as I poo-pooed it as not a very interesting example. Nobody said that these things are... the x has to be an element from anything at all. So no, I shouldn't be surprised that we're now plugging in elements that are not in z, right? Because who said anything about that? I guess this is relevant if you're trying to solve polynomials and you've got real coefficients, but you're thinking about complex roots. Because just because the coefficients are real, you shouldn't limit yourself to just considering x to be a real number. Anyway, this lecture brought to you by 2x minus 1, which polynomial that's really scared me. Okay, and there's some matrices which I'm not super interested in right now. There's a time. Okay. Oh, look at these. Brilliant stuff. Fine, good. Chinese remainder theorem is this. Oh, right, okay, we get algebra on ideals. Given two ideals, say their coprime of their sum is the whole R. That is weird. What do I expect coprime to be? Oh my goodness, because so this is if they have this. So why would their sum be R? If for all R in R there exists I in I and J in J, with I plus J equal to R. But what does it mean for an I in I? Oh, it could be anything, right? Because these ideals might not be principal. If they're principal ideals, then I was going to say they're multiples of things. And then it looks a bit like the zoo. Well, we'll get there. Maybe. Okay, so if you've got coprime ideals, then you can do this brilliant thing. Well-defined isomorphism. Okay. And the proof, I think, is just checking things. I intersect J, which is just things that are in both. This is what you would want it to be. Things that are in both. And the product down here is, oh gosh, why is it sums of things? I guess ideals are closed under summing, so you should probably add these things together, but not multiples. I guess those things are already closed under multiples by R. So fine, okay. Why is it sum up to n? What's n? Some integer n. I guess for any integer n, maybe? Any finite sum? Not sure. Should be an n in there, probably. Further. Okay. So, if you see something where R quotiented by I and J, is that an ideal for the intersection? The following ideals. There's a big claim here. That's an ideal. You check it. If you multiply, then it will be in both. Fine. Is it closed under addition? Well, if you have two things, they're in both. So each was closed under addition, so their sum will be in both. Okay, fine. Being an ideal is pretty straightforward, really, isn't it? You respect multiplication by anything, and you're closed under addition and multiplication. And additive inverses? Yeah, sure, you have those as well. Kind of the property of having is.
For that, you'll have to turn off aeroplane mode.
Yeah, that's why I didn't want you to. We've now triggered the live streamers combo of triggering a smart speaker and a phone. Phone's on aeroplane mode. Shouldn't be doing that. I just completely lost my flow now as well. The process of having something is respected under intersection, so that's all right. Okay. What are we doing? More proof. Okay. Oh gosh. Example: determine the inverse. From Z, this doesn't sound important right now, it's all integer calculation stuff. Ugh. Oh, right, okay, look, and then there's some examples of polynomials down here as well. So what have we got? This looks important to me because quotienting by polynomials is... Well, I care about polynomials more than I care about whole numbers this week. Quest for the Quintic. What are we doing? So factorise a polynomial, fine, and then there's this step to say that generated by the product. So this ideal is things which are multiples of x minus 1, and this one is things that are multiples of x squared plus 1, and this ideal is multiples of both. Crucially, those things are coprime. You can't always go from saying multiple of AB, so it's a multiple of A and a multiple of B. No, wait, the other way around. If it's a multiple of A and a multiple... Maybe these things are just the same. Hang on. Is it important that they're coprime? Let's rub that out and think. Because... No, they're multiples of... If it's multiples of the product, it's got to be a multiple of each of the things. If it's a multiple of each of the things... Oh... It doesn't have to be a multiple of the product, does it? If you're a multiple of 6 and you're a multiple of 8, you don't have to be a multiple of 48. You could be the number 24. Example with whole numbers, up near the whole numbers. Let's try and keep those whole numbers. Let's keep the whole numbers kind of safely above that dotted line. There we go. I think it is relevant that these are coprime. I'm going to write coprime over here. And then this fact is the Chinese remainder theorem, doing some sort of coprime thing. Why is it 11 over there? Definitely not supposed to be 11. Good, and then, okay, fine. That one's R and that one's C. Okay. Ooh, that one's R because of function evaluation. Maybe that was a good fact all along, and I mistook it for a boring fact. Oh, yeah, of course, snazzy. You see this, you say, oh, that's just R. Direct sum, C. Good. Excuse me. Yeah, so this coprime thing is going to come in right here, which says that you've got to put it into coprime. Coprime things. Would be misleading to write something like 4z intersect 30z, because that set also includes multiples of 60, even though 4 times 30 is 120. So it's kind of not enough that for this step, I'll highlight the same step. For this step, it's not enough to just write down two things that multiply to 120. They've got to be coprime numbers, and here they've got to be coprime polynomials, which we haven't really defined yet. I've realised there are more whole numbers down here. Ugh. Work out that it's isomorphic to this whole string of stuff. Good. Okay. Section 2. Woo. 2 hours of live streaming. You get some sort of award, I think, if you do enough in a row. Or maybe they took that away. For a while, Twitch was rewarding people for doing insane amounts of streaming. And my first ever Twitch live stream, 2 hours in, definitely feels insane. But hey, we got some highlights. We got some clips. We haven't clipped the things. We've got, what have we got? We've got more understanding about polynomials and the idea of quotienting for things to be equal to 0. Probably want to go into more detail on that at some point this week. Make sure we properly understand that. And how that can give you these things where there are no imaginary numbers, and things kind of isomorphic to complex numbers. So you can kind of discover them along the way. I've triggered 2 different voice assistants, and Almost lost my voice. 1 hour into the week, which would be pretty bad. Bit of coughing. Excuse me, that's horrible. Right. More about ideals and quotient rings and field extensions, which are, we care about those. Field extensions are, I think, the thing about adding in these extra radicals and extra roots. Let's read. A lot of reading on this stream, isn't there? Okay. Proper ideal. Oh wait, I've already skipped a definition. No. Ideals closed under additional multiplication. What are we talking about? The ideals of R that contain I and the ideals of R quotient I. Okay. The ideals of R that contain I. So if you can contain I, then I think maybe you just contain a few other things as well, but this makes it sound like you contain loads of stuff, because an ideal of R quotient I sounds quite large. I is an ideal of J, oh my goodness. As it's still closed under additional multiplication by elements of J. Phew. Further, oh my goodness. Pi of J, so take the quotient map. Oh, right, okay, just use the quotient map. J bar is the pi of J. So this is a little bit awkward. This is taking pi applied to each element. Each element of J. To get J quotient I. And that's an ideal. Is it? No, I'm confused. Oh, wait, how does that quotient map actually work? It takes each thing to the coset, right? I'm just confused that those cosets live in R quotient I. I think of J quotient I as something kind of different, right? I guess it all works out. I might need to write this out at some point with more notation, more steps. Okay. Needs to correspond to the ideals. Fine, okay. Right, okay, not certain I understood that, but hey, we'll come back. Proper ideals to be prime. Okay, prime ideals. Whenever AB is in I, then A is in I or B is in I. Right. Okay. Prime. Whenever AB is in I, then A is in I or B is in I. So your products. Oh, you get products where. So if A is in I, that's kind of like, well, yeah, AB is in I. But the other way round is like saying, think about everything else for A and B in the ring. And the thing I'm supposed to imagine, I can see all these sixes up here, is probably proper ideal of a ring. Okay. I'm just thinking about the way that 2 times 3 is 6 and trying to make that relevant, right? 6 isn't a prime number. Can I say something about this? So, I guess kind of 3Z. Yeah. Okay, here we go. 6Z, 6 times the integers, is an ideal of ring R. But it can take. But there are things like 2 times 3, which is in that ideal, but neither of those things are. Okay. But if we put 5 there, then I'm talking about a prime number, and this feels a bit more like prime factorized, but like a kind of. The way that if you divide, let's write it out. If I is 5 times the integer, say multiples of 5, then what do I want? I think this is a prime ideal, because if AB is in I, that ideal, then AB is a multiple of 5. So either A is a multiple of 5, or B is. Which is like this kind of prime fact that 5 divides AB, then 5 divides A, or 5 divides B. Which is kind of different to how you normally first meet prime numbers, but it is true about prime numbers on the integers. You have, if your prime divides the product, then the prime divides one or the other, or both. Okay, so prime ideals. I think this needs to go on the notes page as a kind of summary thing. And I can see maximal as well, but let's do prime first. So what's this going to say in the log over here? Can't multiply to get into a prime ideal? That's kind of weird, isn't it? Let's do it like if AB in a prime ideal, then A or B in that ideal. That seems good enough. Okay. And there's a maximal ideal down here as well. The only ideal of R to strictly contain I is R itself. Note R is not maximal. Okay, fine. The only ideal of R to strictly contain I is R itself. Okay, so fine. This feels like a sort of caveat that's not important right now. R itself, so R is an ideal of R. Closed under multiplication and then addition multiplied by R. That's the same thing as being closed, isn't it? The only ideal of R to strictly contain I is R itself. Okay, so it always contains R. Kind of trivial containing. If you try and put anything else in, then you get everything. Fine, okay. Maximal ideals can't be augmented. Maximal ideals can't be augmented without including everything. And technical note, R is not considered a maximal ideal or something. Okay. Proposition 94 looks good. It's a link between several things we've seen this morning. I is prime, if and only if. I is prime is such a weird start to a sentence, isn't it? If and only if R quotiented by I is an integral domain. And here's a proof down here. Suppose that these things multiply to give 0. So this is what it would mean for a 0 divisor in R quotient I. These are elements of R quotient I. This is the 0 in R quotient I. Right, and then consequences. RS is in I. Why is RS in I? So RS, these are elements. So this is like R plus I, S plus I. And when you multiply them, considering elements of I to be equal to 0, so the only leftover bit is the R and S bits. Let's write that out. R plus I, S plus I. This is what happens if you skip the some sort of multiple of I. So it's like R times I, which is something in I. Something in I. And if that itself is something in I, which is what 0 bar means, something in I plus nothing, then that would mean that this RS thing is also in I. And okay, I've got this far. That much thinking to understand one word. And so, because this product is in I and it's a prime ideal, R is in I or S is in I. Why is there a dot? But this is equivalent to, yeah, okay, fine. But that's what it means for R bar to be 0 bar or S bar to be 0 bar. It's a lot of like definition of what the quotient ring is. These bars again. And in the middle we use the definition of prime. Okay, I quite like this as a fact. Let's put it in the notes. And this is going to be if and only if R cross I is I integral domain. That's not a great note, the other one's better. That's a little bit coded. Okay, and then maximal ideals, if and only if R quotient I is a field, which is sort of even better. Wait, so this means, okay, there's a consequence of this. Say I is maximal, give me another one that's not equal to 0, then the ideal generated by both of those things, everything in I and generated by R. Bit mixed notation here. Generated by, this should be like all the elements of I, anyway, never mind. Strictly contains I, and so I have no maximality, that's going to be everything if you give me anything else. Maximal ideals can't be augmented, so if you try augmenting one, you'll get R. So consequently you can make the identity right, and now we're done, right? Yep, okay, we're done up to an element of I. We've made the identity in the quotient group. So R is unit in R quotient I, and that was general, so it's a field. Let's correspond to, okay, conversely, suppose it's a field. Oh, it's an if and only if, so we've got to go both ways. The only ideals are, wait, so fields have rubbish ideals. Fields have rubbish ideals because if you're an ideal in a field, then you're closed under multiplication by anything I show you from the field. So if you've got anything non-trivial at all, maybe your ideal in the field is just 0. Fine, can't do anything with that. Multiply it, get 0. Add 2 things in it, still 0. I have to pick 0 twice. Multiply 2 things in it, still 0. So that could be your ideal. But if you've got anything else that's not 0 in your ideal, then I can, by the rules of ideal, take anything I like from the field, including the multiplicative inverse of your thing, to get 1. So 1's in your ideal as well, and if 1's in your ideal, now I can take anything else from my field, multiply by 1, and that'll also be in your ideal. Fields have boring ideals. Feels like it might have been in the notes and I skipped it, but let's put it on the list. I've remembered I have a list. Fields only have boring ideals, like the 0 ideal with just 0 in it, and the whole thing. Okay. What next? Right, okay, so those ones boring, so it's maximal. Okay. Yeah, corollary. Maximal ideals are prime. Can be proved directly, which we should do at some point. Yep, I think I've said this out loud. The prime ideals I've said are prime multiples. They've got that property that if 5 divides a product, then 5 divides A or B. Maximal ideals are also PZ. Hang on. Oh, but not where P is 0 or P is 0. Because that would just be the 0. Wait, what is P equals 0? It's just the set 0. That's prime, because if 2 things are multiplied, then if 2 things multiply to give 0, one of them has to be 0. Huh, that's integral domain. Ooh, okay. So the question is the set with just 0 in it a prime ideal? It's the same as asking whether your ring is an integral domain. Okay. Maximal ideals, as I said, are, that one's not maximal because you could put in other ones. Good, okay. Yeah, here we go. Ooh, and here's a weird proof. So, example 97, see the problem sheet, which we haven't looked at yet. The ideal is not prime in QX, as when you quotient, get Q squared, can kind of see that. You'll get kind of... Where does that come from? So I kind of want to calculate that the slow way. Anyway, that's not an integral domain because Q squared contains things like 1, 0, 0, 1, which multiply pointwise to give 0, 0. If you multiply those, you get 0, 0. But neither of those is 0. It's not an integral domain, so it proves that it's not prime. Interesting. Okay. The ideal blah is maximal in Q as that in the field. Okay, fine. So it feels like we're going to use that quite a lot. I want to get the maximal facts down as well. Maximal field, so what was my maximal thing? Maximal ideals can't be augmented. All of the ones on this sheet of kind of summary notes have like loads of caveats. Maximal ideals can't be augmented, and that happens if and only if our quotient I is a field. That means that... What does that mean? Which way around does that mean? Maximal ideals are prime? Yeah, maximal ideals are prime. It's a snappy statement there, 95. Okay. Good example from number 6 on the sheet is to go and think about Z2 quotiented by this. I'm not that bothered about Z2. Fine, okay, apparently that's a field. Looks like quite a small field. It's only got 4 elements. It's going to be the field of 4 elements. Anyway. Okay, so in a field, every ideal is principal. It's nice, isn't it? And an ideal is maximal if and only if the polynomial P is irreducible. We're now talking about polynomials. We were in A as well. I forgot to pronounce the square brackets. We're talking about polynomials, so this is relevant again. And F's a field. This is very much relevant, isn't it? Okay, every ideal is principal. Oh, here's the division algorithm. So this is Euclidean division, where you start trying to do, you divide, you have a quotient and a remainder. Okay, so you run that down until you get ooh, as R is in Q minus Q, we must have R equals 0. We'll take the one of least degree, right? Cool. Okay. Oh, A. Take an example of a polynomial with least degree. That could be multiple because I is closed under multiplication by elements from the ring. The ring's a field in this case. Field involves multiplication by loads of stuff. So we've got lowest degree polynomial. Okay. Concept of degree coming in clutch. Oh my goodness. What's part B? I've already forgotten what the thing said. Ideal is maximal if and only if p of x is irreducible. And we got a definition of irreducible there. Cannot be written like that. And Bezout's lemma's right, so we're really using division and Bezout here. This feels too advanced for this moment of the stream, but hey, whatever. Oh, I kind of skipped this, I think. Or maybe it's coming up. Euclidean domains. Okay. Oh, look at this proposition 100. This is such a kind of word soup, right? In an integral domain R, in which every ideal is principal, there's a word for that, I think. It's one of my acronyms. Non-zero prime ideals are maximal. So this is like a reverse of the statement at the top of this page that said maximal ideals are prime, and this is a bit like saying prime ideals are maximal, but there's non-zero in there. We saw near the top that you can't be, oh, not this page, oh, this page. We saw near the top that you want non-zero, And there's some conditions. Z is kind of nice. So there's a condition down here for us to be an integral domain. Proof looks pretty technical. Contradiction is this really date I. Yeah, okay, it doesn't look that surprising. All we've got is that R is an integral domain. Cool, right, I will study this at some point. Overview, believe it or not. 2 hours in. Any reduction of a cubic polynomial? What on earth is going on? Oh, so some sort of example. Irreducible polynomial. Every coset has a representative like that. Where, okay. So, if you're quotienting by this cubic, then whenever you take a really high degree polynomial, you could use some multiple of this. You could start doing polynomial division. You always do that on this. You could start doing some polynomial division to get it down, to get a representative like this, kind of like the remainder. Going to be a question later on, can you always do polynomial division? Since x squared plus 1 is irreducible for Z3, oh my goodness. Okay, so these things don't factorise nicely or whatever, and that. Oof. What are we doing? As it has no roots in Z2, I don't understand this example at all. Similarly, these are 2 examples over different rings. Oof. In the first case, we identify Z2 with 0,1 in FA, it's prime subfield. Oh, that was the thing generated by just adding 1s together. And similarly, we can, in Z3, identify 0,12 as a subfield of F9. Gosh, okay, this is a thing about. So these polynomial rings have. Here we go. The polynomial rings on the top there, in each case, have coefficients from modular arithmetic, the polynomials in X, and in each case we've picked a polynomial and we've quotiented. We've said, what if that polynomial doesn't count anymore? That polynomial means 0. So if you see a complicated polynomial, then well, put up some factors of x cubed plus x plus 1. Just keep going. Those are all 0. Ignore all of those. You'll get some leftover stuff. And you end up with some sort of weird structure, which is a field. Why is it a field? It's a field because the ideal is maximal. It's maximal because in this ideal, oh my goodness, right, okay, there's a lot of things strung together here. The non-zero prime ideals. Okay, some conditions on the ring itself, the polynomial ring itself. Every ideal is principal, non-zero prime ideals are maximal. Yeah, okay. Gives you a field. And this, I think, is being used to generate interesting fields. I've slowed down a lot because I've seen the phrase adjoining a root, which is, oh my goodness, sounds pretty much like the Quintic thing, right? Adjoining, like adding roots of polynomials, something I care about quite a bit. We're looking for the roots of a Quintic, and I think we're going to, later this week, have statements about when you try adjoining things in a particular way, then you can't have kind of all the roots of the polynomial in there. Something. We're nowhere near the Quintic. Let's look at 102 here. There it is, just off the top of the screen. F field and f of x being an irreducible polynomial, one which you can't split into factors, then this contains an isomorphic copy of f. Okay, so then you've made a new field, k, which contains an isomorphic copy of f, like the constant polynomials, I guess. And there is a root. Oh my goodness. There is a root of f of x in K. That's very surprising because f of x is a polynomial. Plugging in an element from K, I guess maybe I shouldn't be surprised that we're plugging in elements from whatever. It's just a polynomial. Who says x has to be anything, right? Cool, okay. So irreducible, so maximal, so field. K is a... Okay, so we've got a field that contains an isomorphic copy of f when you think about function evaluation, which is... so it's not just looking at the constants. Yeah, identify f with the cosets. So this is an element of f, and then this is a coset, and a bar. Right. Oh, okay. Hang on. No. Why does this work? Why can you identify these? Wouldn't these be all different depending on? Wait, this is ideal? There's no properties on A? Just A as anything to do with F? Maybe I need an example. A plus the ideal generated by f of x. Generated by f of x. So for those examples with like x squared plus 1, a plus the ideal generated by x squared plus 1 would be p of x, x squared plus 1 plus a, which is a bit like factoring out I or something, right? And minus I at the same time. But factoring out some sort of new root. So the thing that doesn't, it's irreducible, so it doesn't have roots in f. But to try and factor it out anyway, be left with some remainders. Those are the cosets. Now we can identify that element to say, look, okay, everything in your polynomial ring, not everything is a multiple of a squared plus 1, that'd be ridiculous. But wouldn't the remainder maybe have some like b of x on it as well? Oh, it contains, yeah, sure. Okay, so there's loads of stuff in there. Loads of stuff in this K thing. K's massive, but in particular it contains things where you add. So these are like the okay, they are the constant polynomials after all this, kind of. The constant polynomials don't actually live in the quotient ring, but the cosets corresponding to those constant polynomials. So these are cosets corresponding to constant polynomials. Woof, that took a lot of parsing, right, to understand what was going on there. K contains loads of stuff, probably. But in particular it contains constants. You can't just say constants because the quotient ring is all about up to an element of the kernel, up to an element of this thing you're considering to be 0. So it contains loads of extra stuff. So you kind of have to add on this plus stuff generated by f of x. So that's just what things inside K look like. But we've chosen to look at here constant polynomial on the left, element of f on the right, constant polynomial. Those things are the same shape. All fine. Can you do this as a... Is this like kernel image of a function evaluation thing? Yeah. This is kernel image of... This is first isomorphism theorem, right? So phi goes from f of... This is exactly the map that we've seen before to k. Yeah, phi goes from f of k by a plus ideal generated by f goes to a bar. I think something like that. A goes to... What do I want? I want this to turn out to be the kernel. Ooh. Yeah, it's not quite, is it? So I wanted this to be like the kernel of some map. And then this is like the image would just be F. Does that work? Can I plug in? Obviously there's anything I can plug in, right? I mean, here I'm thinking I, but you plug in a root of the irreducible polynomial. Okay, anyway, what are we doing down here? There is a root. There is a root of f of x in k. Consequently, we can make sense of p of k. Oh, right, okay, we can make sense of it by just doing the normal thing, right? In particular, f of x bar is f of... Oh my goodness, look at this. So x bar, things from k. This thing is things generated by f of x. So f of x plus, and then f applied to something from here. Because, oh my goodness. So why isn't there an f around the outside of this thing, right? There's so many brackets here. What do I want to do? Close the round brackets for the f of x. Close the pointy brackets for the ideal generated. Close the round brackets. Make it look rounder. Close the round brackets for f. That is just a combination of things in the ideal generated by the f of x, and ideals are really closed under that sort of stuff. So if you apply f to it, f is just sort of a combination of like take these elements and like square them, cube them, multiply them by elements from f, add them all together. That's nothing. That's just in the ideal. Ideals contain loads of stuff. So that's just something from the ideal, which is kind of mad. And then also this is something from the ideal. F is... Why is F being applied to each of those separately? Oh no, maybe I'm wrong. Yeah, I've kind of applied F to each separately. That's not quite what's going on, is it? There's something more like binomial theorem or something. Yeah, it's not even quite F. It's not quite F because there's some sort of binomial stuff going on here. Like if F involves squaring, then you get x squared plus x f of x brackets. To x f of x plus something from this thing squared. So there's actually a really complicated polynomial applied to this element here that involves multiplying by x's as well as numbers. But that's fine, that's still something in the ideal generated by the f of x. Huh. What was I doing? I don't know why that means there's a root. I don't know why P's here and F's down here, never mind. Why does that mean that it has a root? Oh no, so this ideal is equal to 0? Why is that ideal? Oh no, the ideal generated by F is the 0 in K. So the 0 in K, K is the quotient group, quotient ring. Which the 0 in the quotient ring, we're considering anything that's multiple of F to be 0 in the quotient ring K. That means that f of x bar is just 0, like for anything? Why are we saying a root? I can't see what it matters what x bar is. Yeah, it looks like it's just anything, right? A root x bar in K. Don't get it. is big though. I think I should try and understand this. Yep, we're going to spend 5 minutes trying to understand this. F has a root. 0k for that ideal. So it says that f of the whole thing x bar. Right, f of the whole thing x bar. X bar. All of these bars. F of the whole thing x bar. No, that's not helping me. I've got in the back of my mind. I've got like complex numbers and integers again. No, not integers, reals and complex numbers. Where this would read something like, this is quite exciting. Given the real numbers, f a polynomial you can't solve in the real numbers, then you take the new field, defined like this, take all your real polynomials and quotient, x squared plus 1, that now counts as, ignore anything like x squared plus 1. It's taking me a really fancy polynomial, x squared plus 1. That contains a nice morphic copy of the reals, which is fine. It's sort of a bigger field. It contains all the reals, which is fine. But also it's got a root now. Your new field has got a root of that irreducible polynomial. So this extension this field extension. It's called a field extension. This field extension takes maybe my reals and gives me my complex numbers. Returns me a larger field where I can solve that. I would really like to know how to solve it. So I'm going to try one more time to understand this sentence at the bottom. F of x bar. Okay. This was not super helpful, so I'm going to have another go. F of x bar. So take the whole thing. If I just skip why it's true for a second and read the whole line, it says f of x bar is equal to 0. Has a root x bar and k. I guess if f of x bar is 0k, then it would be, hey, there's x bar. I don't know what x bar is. Is that important? Yeah. Oh, it's the polynomial x. Coset of that. Oh. So we looked at constant polynomials, and now we're looking at kind of linear polynomials? The coset of x. So anything that would be coset, what is x bar, is x as a polynomial, if f of x is x squared plus 1 or something, anything times x squared plus 1. If my f of x is x squared plus 1, my favourite polynomial today. X. Huh. So things that look like x. Wait. So if I had x squared plus 1, then after kind of dividing, I'm left with this new field which contains constants, fine, they look like the reals or whatever they were before, plus x, kind of the solution to my polynomial, things that look like x. The root is x. So given x squared plus 1, we're looking at all the multiples of x squared plus 1. Let's ignore those. Let's imagine that we plugged in something. We plugged in something and we got oh, that's 0. We solved it. We did it. Our root solved that. Lovely, brilliant. Off it goes. That's all 0. Your complicated polynomial is now a very simple polynomial. If you quotient it by x squared plus 1, it's got maybe a linear term and a constant term. Those are polynomials, mate. Awkward. What do you mean you want the number x? Well, okay, fine. Please look at just the x bit. I've got all these polynomials, right? I've got these numbers plus x. I've got 3x plus 2. Do you want any of these? You just want x? Fine, okay. It kind of generates as well. K is large. It contains... right, K contains not just the number I. K contains 3i plus 2 and stuff. Those things are a bit like polynomials. It contains them as... not quite a polynomial ring, a quotient of a polynomial ring. So it's got like, in that case there, it's got like constants and linear terms with a rule for how to combine them together. It comes ready-made with one where if you want to combine those two things together, you're supposed to consider them as polynomials, multiply the polynomials, and then throw away anything that looks like x squared plus 1. That's your rule on those polynomials. So that is kind of a baked up version of the complex numbers. That's C. And contains a root. The root is the new element that we've got, x. Right, okay, understand why it's true. F of x bar, so when you try and plug this thing in, you're trying to apply x squared plus 1 to this. Well, there's some squaring to do, and there's some adding 1, but overall, most of the terms involve this by the binomial theorem, but the x squared plus 1 will live over here, and then that means everything's a multiple of x squared plus 1, so that really is 0. So we get this new field to play with, k, which, fine, okay, it's got bars on everything because it's a quotient ring, but in the new world, we get a root to our irreducible polynomial. We get a field that contains an isomorphic copy of everything we had before. An extension. That's pretty good. There's x. Just look at your x. You want just I? Fine, okay. Go over there. What if you want minus I? So in this case, there's another root that comes from looking at minus x bar. In this case, it turns out that when you square it, you get lucky, and minus x squares the same thing as x, so you can't get lucky in that case. And find another root. Kind of added both. Yeah, sure. Okay, we added both because it's got multiple roots. It's irreducible, and we extended and it gave us c. C then happens to contain another root. You might get multiple roots when you extend the field. Okay. Good. I like it. That felt like a clippable moment, but whatever. I haven't worked out how to clip things. And there's no one in chat, so whatever. The polynomial x plus 1 is irreducible in Z2. Again, how much do I really care about Z2? The things are really small in a way once you've quotiented. You get a finite field. Why is it? Yeah, okay, fine, okay. Nothing surprising anymore, right? Ugh. We know that y is the root of this. What are we doing? Okay, fine. Right, okay, we're using y, so okay. How much do I care about Z2? Not a huge amount. X cubed minus 2 is irreducible over q. That's nice. Cube root of 2, not a rational number. If we set alpha to be the cube root of 2, then we get things look like this. Fine, okay, because these polynomials, like these are like a bit like polynomials, right? But if you went to alpha cubed, then we'd say, aha, no, alpha cubed is 2. That gets to be part of q1. You can factorise it. Oh my goodness. The other two, which is complex and k, is a subfield of R. Oh, okay. So, bringing in the cube root of 2 by doing this, which I guess we built by doing polynomials quotiented by the ideal generated by x cubed minus 2, cannot factorise further. The other two is complex and k is a subfield. Okay, so the other bit, this is irreducible. And even irreducible in q of alpha, q root 2. Okay, here we are then. We got definition of field extension. That's one page ahead. K of f is a field which contains f as a subfield. We denote this extension as k colon f. Big thing on the left. Okay. Let's go here. Let's get this notation. Field extension k of f, k colon f, k f are both fields, and k in F. Cool. No, the other way around. F is in K. Slightly annoyingly, when you write division or something, right, that big thing goes on the right, whereas here we got the big thing on the left. Fine, okay. Degree of the field extension. Oh my goodness, hang on. We got a vector space. Thought this would happen. So this is like how complex numbers are a bit like vectors. Why is it a vector space over F? So to be a vector space, you need to have some sort of field where you can multiply your vectors by that field and do, add things together. And because K is a field, you're just allowed to do all that stuff. You're allowed to do all that multiplication and addition. It's just fine. All the stuff you would need to do to be a vector space. By, in particular, things in F. So this is kind of a bit odd, really. Let's do C and R again. C is, the complex numbers are so nice, everything's got an inverse you can multiply and add, that it's fine to consider all of the stuff in C as vectors over the reals, so that when you try and multiply a complex number by a real, of course you can multiply by a real, because reals are complex numbers and you can multiply those things in the field of C. But you can also do things linear combinations, add them, it's all fine. So if you've got a subfield, it's vector space. Then there's the concept of dimension, which feels important for the notion in which complex numbers are a two-dimensional vector space over the reals. And there's a basis, things like that. Okay, so we might need to understand the bases along the way as well. Okay. Countability is in here as well. Vector space to Q then. Yeah, any finite degree field extension of Q would be a vector space of n. If it's got finite degree, then there are n basis vectors. So you could represent anything in there with something from a Q for each of those things. So the size of that would be Q to the n, but that's countable. Oh my goodness, okay. Very technical in B there. Field extension to degree 2, degree 3. Feels like this degree. I would like it if, is this related to the degree of the polynomial that we quotiented by? Up here, degree 3 polynomial. Previous page, degree 2. Be nice, wouldn't it? This one's degree 3 as well. This one's degree 2. It seems to match the degree of the polynomial. I don't actually know if that's true or not. I suspect that there's something going on there. Right, here are some Galois fields. Galois in coming up to the 3-hour mark, and we finally met Galois. Field of order p to the n for each prime p and positive integer n. Okay, fine. Oh, finite fields always have that order. Oh no, right, okay. As a field of characteristic 0. Get that. What? As a field of characteristic 0, that doesn't sound like a finite field, right? If it's got characteristic 0, because you keep adding 1. You never get back. Generate new stuff. Right, so this is just saying it's infinite. So instead, f has characteristic p and contains zp as prime subfield. Oh, that's the phrase for when it's 1 plus 1 plus 1. Like the smallest one? I need to remember what prime subfield is. F is the field extension of some degree n over its prime field. Right, fine, okay. As a vector space, there we go. This idea that as a vector space you've got a basis, so you pick up all of these items. It's your coefficients in that vector space. You need n of them for an n-dimensional vector space, but that's not too bad. There's not that many things. Okay, finite fields. They've got orders p to the n. It's pretty good. There's no finite field of order 6. It's pretty good, actually. It's pretty good. You wouldn't think that from the definition, right? So, field, you can add, subtract, multiply, and you can divide by any non-zero element. And therefore, your field does not contain exactly 6 things. This is kind of good, right? It's not obvious at all, really. You think, well, can I just take my 6 and define their inverses and make sure that addition works nicely and they're always distributive and associative? But no, that's impossible. Because I'm going to look at first what happens when I add 1 together in your field. 1, 1, 1, 1, 1, 1. And that's going to form a subfield. Maybe you got some extension over that subfield. Yeah, so 6. If you're trying to do 6 elements, then I think basically you have 1 together and you'll get some factor of 6. But then you can't extend it. Yeah, I can't do it for the case 6. That's what I think that's over here. No field of size 6. No size 6 field. Good fact. And then Galois says there's actually one of these by demonstrating there's actually an irreducible polynomial. It's off syllabus for these lecture notes that I'm looking at. At some point I might go and try and learn why this is true. Galois fields. Multiplicative group of any finite field is cyclic. Oh, boring. Hang on, is that because of groups? Can be computationally difficult to find a generator. Let's not go there. Oh, use it for cryptography. Good. See how this is suddenly interesting, right? We've got 2.5 hours, which took longer than I thought. 2.5 hours of kind of trudging through definitions of rings and principal ideals or whatever, and then suddenly we've got a strategy for generating the complex numbers and other stuff like Q root 2, and we've got the fact that there's no field of order 6. Plus, by the way, hey, why not use these particular ones for cryptography or something? How to generally make fields. I just think sometimes on the journey, let's go back to the map. Sometimes on the journey, on the quest, you can get really stuck in like the mines of Moria or something around here, where you're underground, you can't see anything, it's dark, and you gotta fight a Balrog. And then sometimes you're just on the top of a mountain, right? You get to the top of a mountain, not the big one, you get to the top of a mountain, and you can just see really far. Suddenly you can see, oh my goodness, over there, complex numbers, field extensions, pools of lava, which I drew quite far away, and we're already there. Got to understand them, that's the hard bit. More lava, good. Steam, there we go, okay. You can sort of see further and say, right, okay. Beat the Balrog, what's next? Like the bit at the end of the Hobbit movie where they see the mountain. I'm going to refer to that quite a lot, I think. I was just pretty cross when there's 3 movies, right? They're making 3 movies out of the Hobbit movie, and the first one, you get to the end and they just see the mountain. It's a film that you can't spoil. There's no spoilers for the movie because what are you going to say? What are you going to tell someone? Like, well, at the end of the movie they see a mountain. Like, no, terrible. Anyway, that's fine. I can have all hot takes in this because nobody's watching. Certainly nobody's going to watch 3 hours of VOD. It's more of an art project, really. Plus, I'm getting better at Twitch. Maybe I should learn to use the clip that button. This is the longest live stream I've ever done. Oh, open days. Open days. How long was I live for on opening? Maybe 3 hours. We're going 3.5 this morning, so we'll see. longest time I've been talking to a live stream for. My plan for not talking to myself was I had a little soft toy balancing next to my camera. 2 minutes in, the soft toy fell off the back of my computer and has disappeared. So there goes that plan, right? Like the kind of rubber duck thing where you talk to a rubber duck, except gone. Right, this is a solution for generating a field of 16 elements. Oh, I can just look at this. The generators are like this, the polynomials, just a bit of a mess, aren't they? Preferred representatives. Okay. Right, down here. Minimal polynomials. I like those. Right, given a field extension and a number in K, is it a number? An element of the quotient ring, fine. We say that alpha is algebraic over F if there's a polynomial in F. Oh, like a boring old... Right, fine. Unsurprising number. We could already solve for this. Sort of. So like, in K there's a copy of F. So in particular, things in F. So like, things in F are not where you should look for algebraic numbers because they all satisfy things like this, which is in this polynomial is in f of x, and has f of alpha equals 0. So like members of F, super boring. You don't go there. But look further, and you might find some other things that are not algebraic, like how in our complex number extension of the reals, we found these items that are like I. I guess the notation there is coming from algebraic numbers, like roots of polynomials. Might you consider I to be algebraic or not? Depends which field you're talking about. Algebraic. Where have I had that before? I think I've had it as the root of any polynomial, which kind of makes sense, I guess. That's what this is saying. Root of any polynomial. Any polynomial. Huh. Like, people say that pi is an algebraic number because it's not the root of any polynomial. So it's a little, like, sidetrack here. Pi is algebraic. We may gain a way to understand that fact a little bit more. Okay. Proposition. There is a unique monic polynomial. Monic means coefficiency unit. The leading coefficiency unit. Possibly identity? Unit? It's field gone. We're in fields now, aren't we? We're in fields. Unit was 1. Monic polynomial in f of least degree such that m of alpha is 0. Okay. So there is a polynomial. Yeah, no, hang on. If you're algebraic, then there is a polynomial, fine. Take one at minimal degree, fine, okay. For f in big F, goodness me, for a polynomial, we have f of 0, 0, even only if m divides f. Oh, this is the irreducible. This is the ideal generated by the minimal polynomial. And mx is irreducible because if you reduced it, you would get two things which multiply together to give. Well, we'll get those on the page. Something to category equal to the m of. Oh, yeah, this is what I wanted, I think. Yeah. This is the field extension, right? No. This is. What is that? Right, okay, well, we're going to get that. As there exists a polynomial f of x such that f of a is 0, f of alpha is 0, then there exists. Yeah, okay, boring. Division, whatever, yeah. Division algorithm again. God, this is always okay, fine. As k is a field, here we go, okay, so interesting stuff. Further m is reducible, here we go. If m were reducible such that you could do this, then we'd have this thing is 0, but k is a field, so it's an integral domain. Ooh, okay. So one of those is 0. Minimality. Okay, so this turned out not to be that exciting anyway, after all. The last bit though, subfield of k of degree equal to the degree of f of m of x. I think I want this to say something about subfield of degree. I know we were talking about degree of the field extension over here. This is subfield of degree. Fine, okay, maybe that leads to the same thing. We already certainly F. Certainly F is yeah, okay, that's a ring. Commutative ring with an identity. It only remains to show that the non-zero elements are units. So it's a field? I want to know about the degree as well. I want to know about the degree. Right, good, okay. M of x does not divide g of x, and as m of x is irreducible, it follows that g of x and m of x are coprime. Pazoo again, here we go. Back up. What are we doing? F after the subfield of k. G of x and m of x is a coprime. I don't understand this, what the page turn's not helping. Say that this thing is a non-zero polynomial in this space, then mx does not divide g of x. I'm so lost. Well, it's non-zero, so if m divided g, then it would be 0. And as m is irreducible, follows that g and m are co-prime. They don't have anything in common. By Bazoo's lemma in F, we know that there are. I've got to understand co-prime and irreducible a little bit more. These are not comfortable right now. We know they're polynomials u and v such that those things combine to 1. Okay, fine. Bazoo. G is a unit. Finally, if n is the degree of m. So g of alpha is a unit. Okay. Up to. Right, because m of alpha is 0. So u alpha, g alpha is 1. We see g alpha is a unit. Finally, if n is the degree of m, f of alpha is in. Okay, take some polynomial in this thing. We're going to talk about the degree. See from the division algorithm that f of alpha is r of alpha. In the span of, oh gosh, okay, here's the vector space. N is degree m. So, right, this says take f of alpha, some horrible polynomial with alphas in it, and try and divide it by, so use the division algorithm to try and divide it by m to get down to something that only uses polynomials up to alpha to the n minus 1. Okay, so take your big general polynomial, scary, and do this division on it, right? We've got m of x, that lets us bring down the degree until we get down to degree n minus 1 or lower. So this kind of span of things is like polynomials with limited degree. Which is not a ring because we haven't met it before. It's not a ring because you can't multiply, your degree might go too high. That does make me think about looping the degree around. Not today. Could you loop the degree around? Oh, it's going to give you 0 sometimes. I'll deal with that. Could you loop the degree around? It's mad, but I think it'll probably work. So degree. Consider. Yeah, it's like quotienting by an infinite series. Anyway, never mind. Not now. So those are a basis for f alpha over f. So n is the degree of that. Ah, right, okay. What do you mean as well? Ah, okay, so the basis of the field extension of f of alpha over f. Is that what I wanted? I kind of wanted to talk about k, right? What's k and f of alpha? What's the relationship between k and f of alpha? Oh, so k might be huge. K might be huge, it might include loads of stuff. But f of alpha is just like picking out one thing. Show me just one interesting element that you've got, like cube root of 2. In Q, no way. K is massive, Q of cube root of 2. So then we're just talking about maybe maybe K is like rational numbers, but I threw in cube root of 2 and I as well, and also something else like pi. Actually, not throwing pi. No, I've thrown pi. So it's a huge, but you can choose one particular thing, like alpha is the cube root of 2, and talk about the field extension, talk about the degree of the field extension of f of alpha over f. Degree of that would be 3. And that does correspond to the minimal polynomial. So it says if you're just adding in one, if you just want to add in one number, like one root of a polynomial or something, show me the minimal irreducible polynomial, monic, why not? And then show me the minimal irreducible polynomial. And when you do the field extension, just throw that element in. That's the degree of the extension. I haven't quite got with why the field extension. Right, we've met field extensions twice. Excuse me, sorry. Back here, just a tiny bit. We had them here, where it was anything that contains the other one. And we had some stuff over here which I got very excited by this kind of thing about taking an irreducible polynomial. I suppose that's an example of a field extension. It doesn't have to have anything to do with field functions. But in here, independent by the minimality of m. Yeah, okay. Independent by the minimality. That needs checking. Okay, so this does say the thing that I want. If you throw in x squared plus 1, then when you quotient, so yeah, let's write this down. So if you take real polynomials quotiented by x squared, the ideal generated by x squared plus 1, that's a minimal irreducible polynomial that's monic with degree 2. This is isomorphic to C. There's some little bit of work to do there, but more importantly, it contains kind of something that's equal to, contains f that's something that's isomorphic to the reals, and it contains a root. The thing that's like x bar in this, is a root of the polynomial x squared plus 1 in this world, which is a root of that, which is great. What am I doing? Degree or something. Like the degree, how large is this vector space? Is 2. The degree of that there. Cool, okay. Am I allowed to write this as like Ri? Probably. I don't like it though, so I'm going to not do that. Okay. F16 I don't care about very much, so I'm skipping forwards a little bit. Okay, 27. Tower law, brilliant. Okay, let's go. Love a tower law. If you nest them together, then they're vector spaces. Okay, this looks fine, really. You multiply them, they're a little bit like fractions. This is probably not a helpful thing to say, or a helpful thing to think, but these fractions would cancel. Yeah, let's erase that before anybody sees it. So take your bases and then construct a big basis for the big thing, right? And also go the other way. Yeah, fine, okay. Dimensions. Spanning, yeah, it's all vector space stuff. If we're going to understand this, then we need to understand vector space system, probably an I. Yeah, vector space stuff. Good, okay. Find the degrees of the following extensions. That one's got root 2 and I in it. Let's try doing this. Well, let's read the example, I suppose. Minimal polynomial of root 2 over q is x squared minus 2. good. So fine, that's got degree 2. And the next one's got degree 2 as well when you put in I. Oh, yeah, so it's checking that those things are actually different. We got this stuff about integral domain, maximal ideal gives you a field. Can it be linear as that thing? I is not real. Okay, we're using some real number facts in there as well. A bit more care for that one down there. So root 2, yep. But then how do you know that the degree of that is root 2? Because you would need to check that this polynomial is irreducible over that place, which involves checking like a general element isn't a root already. If it reduced, so reducing means writing it as a product of two polynomials, which here, because this polynomial's got a really low degree, here reducing it would mean writing it as the product of two roots. Maybe there's something in that this is the first moment we've seen where low degree polynomials kind of let us make progress. I know, I mean, we've seen loads of low degree polynomials, but pause for a moment here that because x squared minus 3 is quite a low degree, for the polynomial to be irreducible, can't write it as two polynomials multiplied together. Those would have to be, by like degree, those would have to be linear polynomials. If we had those linear polynomials, they would have a root. Yeah, okay. So this is not quite the same thing, right? Being an irreducible polynomial is not quite the same as not having roots, I think. Because, oh gosh, so in just real polynomials, x squared plus 1, x squared plus 2, that multiplies out to like x squared plus 3x squared plus 2, which I think has no roots in the reals, but it's not irreducible. So there's something subtle going on here, where we're just checking if it's got a root. If it reduced, then we'd have, and then we're checking a root. Right? That's what we're doing. Yeah, we're just checking that squaring it gives you 3. But, okay, this is vector space of Q. You look at the coefficients in your vector space. Okay. In particular, look at this coefficient in your vector space. Good, okay. 4. That's interesting. So what am I thinking? I'm thinking at the moment, this is probably not true, or not where this is going, but 5 is interesting because a degree 5 polynomial could factorise as a quadratic times a cubic. The cubic would have a root. What am I saying? Quadratics. It's the first time you would maybe consider having a cubic as well as a root, but the cubic would have a root anyway. But maybe be irreducible? What on earth am I saying? Yeah, okay, so let's say you had some trick for solving quadratics using complex numbers, then you might, at one step during your working for a higher degree polynomial, you might be worried, oh no, what if my polynomial just secretly has some like trivial factorisation? For a quartic, for a degree 4 polynomial, you might worry, oh, what if it just has a root and an irreducible cubic, in which case, well, it's fine, just look for a root. What if it has two quadratic factors, where you would say, oh, that's fine, I can solve quadratics as well with complex numbers, so just look for complex numbers. But for a quintic, you would maybe have to worry about a cubic multiplied by a quadratic? That's just nonsense. I'm just saying you can make big numbers out of small numbers, so everything's fine. This, if anything, this is a demonstration that there's no problem with the quintic. It's just going to keep being fine, because it's just split it down, right? Worry about smaller things first and then build up, which is nonsense, not how this works. The quest continues. This is powerful because this looks like a statement that something does not, right? This field does not contain. That's the sort of thing I'm looking for, right? Quintic does not have. Okay, F16, field I've been ignoring so far. F16 as a subfield K of order 8, we would have that is 3, and so, oh gosh, finite fields. So this degree 8 thing would be a vector space over Z2. We know that F16 contains Z2 because F16 contains, it has characteristic 2, I think, so the identity plus itself is 0 and you have Z2 in there. K as an extension over Z2 would be degree 3 because 8 is 2 cubed. And 4 would be, well, 16 is 2 to the 4. So the extension of 16 over Z2. So the trick is considering there to be like a secret third field Z2. And this is supposed to be somewhere in between F16 and Z2. And that product does not work out to be a whole number. Cool. Okay, we've got some field extensions, we've got some numbers, we've got a thing that does not happen. We've got some ingredients that make me start to think about Quintics. It's pretty good for a Monday morning. Okay, what's next? So, factorisation and stuff. How do I want to play this? So, I think I'm going to do 20 minutes, get to past, and then take a quick break. Come back at 1. I think that's the plan. Now, how do I want to spend those 20 minutes? I think I want to go back and understand something slightly better. We're about to move on to things about factorisation, which feels important. I think I want to go back and make sure I understand some of those key words a little bit better. So I had some exclamation marks in here where I started to feel like I didn't understand irreducible and coprime. Let's see if we can just have 10-20 minutes of getting slightly more happy with irreducible and coprime elements. How do I do this? I think I'm going to try and do a search. Can I do a document search? Yeah, I can. Irreducible. There we go. Search. Searching. Let's go to page 29. Right, okay, so irreducible. That is, f of x cannot be written as the product of two non-constant polynomials. Sorry, it looks a bit like it's censored the word irreducible where it's found it. Oh well. F of x cannot be written as the product of two non-constant polynomials. Yeah, fine, okay. So reducing it would be to write it as two things. Is there a previous? Somewhere deep in the notes. Oh my goodness, right, okay. So it's 1. Have we seen any more mentions of irreducible? Oh yeah, also on this page. 3 has no roots in Z2, so the polynomial is irreducible. That's a sort of cubic kind of fact. Yeah, maybe it's quartics where I start to worry. Quartics where you can have 2 quadratic factors. Yep, and then over here we had some stuff about irreducible polynomials, but we haven't really been told about what an irreducible element is yet. It is funny that it's sort of blacked out the word irreducible. I can't see it on this page. Oh, it's just off the bottom. It's off syllabus remark, and then is there more stuff coming? Maybe it's coming in the next section. Irreducible, 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 irreducible. Next, 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 next. I've been here before. Right, an irreducible element. Where are we? Here we are. This looks good. Is it slightly further than I got? Yes, the next page. Right, good, okay. So, in the choice there between moving on or going back and understanding better, turns out I should have just read on to the next page, where there'll be a definition of irreducible element. What's the other thing? Coprime elements, right? Oh yeah, that's on this page too. Right. Forget what I said. Great use of the search function. It found that the next page was the page to look at. Amazing stuff. Okay, we've got some definitions. A defies B. Yep, cool, just like numbers. We're back to rings now. No sort of field stuff going on. Rings are going to be assumed to be CRIs now. Commutative rings with identities. That is going to make all this multiplication stuff easier. Common factor, good, okay. Highest common factor, and I like this. I've seen this before in number theory courses or something. whenever D is a common factor, then D divides C. That's what it means to be a highest common factor. You might be expecting there D less than or equal to C. D, yeah, but actually D divides C. Just a bit more general, a bit better. Okay, if A and B are non-zero, we say that C is a common multiple. If A divides C and A divides B divides C, fine. Least common multiple, red, good, okay. In an integral domain, remember those, can't multiply to get 0. No zero divisors. Yeah, good. The highest common factor of two elements, if it exists, is unique up to multiplication by a unit. Corresponding result also holds LCMs. Okay, uniqueness. Okay, in an integral domain. How does this proof work? A, B, B, non-zero elements. Oh, right, okay, so H1 and H2. If there are two, fine, okay, they divide each other, unit, integral domain stuff. Okay, example, find numbers. Oh my goodness, highest common factors. Wait, in the Z extended with square root of minus root 3, these have no highest common factor because here are their factorizations. No, what? The factors are that. The common factors are these. Oh, but none of these are the highest common factors because they don't divide the others. So you might think just take the biggest one, but you can't do that on the complex numbers. One divides the other. Huh. Okay. I don't love this. If one is the highest common factor, an HCF. I guess it's and because it's H. Anyway, London. So it'd be coprime if equivalently a unit is the highest common factor of theirs. So that would be if a highest common factor. It's just so annoying to think of, right? I'm going to pretend that the highest common factor is unique up to units. That was what we said, right? Yeah, okay, no, we said that. The highest common factor, where I know which one I mean, up to units. It's like basically one coprime. No, really kind of no common factors, except stuff that has to be common factors. Units always factors? Units are always factors? Yeah, because multiply your unit by its inverse, then your element. So if U is a unit, consider U inverse A. That's equal to A. So U divides A. U is always a factor. So all your units around, they're always there as common factors. Coprime ones where that's it. I feel snappy enough to go on the log. Quest log. Dear diary. Coprime means just units for common factors. Coprime of elements. I think we're going to have coprime ideals. Do we already have coprime ideals? Yeah, once we can add them together. Add them. We've got the concept down here of a prime element. Oh, look, this thing I wrote up here is an explanation of that bit. We've got a prime element where whenever x divides the product, x divides one or the other or both. An irreducible element. Oh, okay, so it's not what I would have guessed. Oh no, it kind of basically says you cannot write it as y times z unless you've got some unit stuff going on. These units are a bit annoying, aren't they? Well, I don't know, maybe being able to invert things is nice, but the units in Gaussian integers are just 1, minus 1, and I and minus I. Okay, so they're kind of non-trivial, aren't they? I was kind of hoping there wouldn't be any, but fine. I guess it lets you deal with negative numbers nicely. Normally when you learn about prime factorizations and stuff, you just do positive numbers, and then people get a bit worried about negative numbers and like negative primes, but this all works for negative numbers. So hey, maybe this gives us a different way to teach prime numbers. So that's not how I was taught prime numbers at school, right? Makes the infinitely many primes thing look more interesting, right? Whenever x divides a product, x divides one or both of them. There are infinitely many things that do that. Crikey. I guess I believe that prime numbers in the integers do both of those things, irreducible and prime. So the distinction is not that obvious. But here we are. In an integral domain, prime elements are irreducible. It's going to be good. And then presumably other stuff as well. So my example about normal numbers z is an integral domain. Prime right, okay. All of these things look like they have pretty straightforward technical proofs. Yeah, fine, okay. I might come back to this. Modulus squared, blah 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 blah. Oh, you can't reduce 2, right? Okay. 2 is irreducible, but not prime. In that space. Okay. Do I want to do these Euclidean domains? Yeah, quickly. We're making really good progress. Skimming through quite a lot of ring theory today, getting stuck into that mountain range. I'm trying to see ahead to where we're going. I can't quite see why all this stuff, which is, to be honest, where I got a bit lost with this as an undergrad. All this Euclidean domain stuff and primes and coprimes, I can't quite see how that's related to the polynomial stuff that I care about, right? It's kind of where I got lost with this as an undergrad. It's also basically the only thing I remember from being an undergrad. Principal ideal domains, EDs. But here we go again. Okay, Euclidean domains have got a norm, and you can do division algorithm on them. You can do the thing where you write it as such that, such that A writes as Q plus B plus remainder R. And that's going to be abbreviated to ED, slightly unfortunately. So integers form one of those, and polynomials, you can use the degree of the polynomial. And this says given a field f, I guess, why are we worrying about being a field rather than just like an integral domain or something? Why do you want inverses? Oh, because you need like top coefficient. In order to start doing this division, you need to be in a field, don't you? Yeah. So you could look at that top coefficient and say 3x squared. That's a bit like 2x squared, but times 3 over 2. At which point, what's that? Okay. What on earth? Gaussian integers. Okay, with the degree is distance. And here's a proof. Oh, the proof is messy and involves the square root of 2. Grid of unit squares. Oh yeah, there's Gaussian integers. I've drew this before. So, what is this then? There exists Q in Zi such that the distance between alpha over beta and Q, alpha beta in C. What on earth is going on? Maybe come back to this. What are we trying to prove? Oh, these things all have quite largely. This is not quite degree of a polynomial, right? It's degree of like the norm. Okay, it might be a mystery for the afternoon. Explain why the Gaussian integers. How much do I care about the Gaussian integers though, right? Maybe not for my quest for the Quintic. Wait, hang on. That sentence at the bottom sounds really cool. These each have infinitely many integer solutions. That's pretty good. Those are... Okay, I have this like dichotomy, right? How much do I care about? Finite fields, boring. Integer equations, lovely. So, those things are extremely related. So I should try and pay more attention, I think. What does this do? D is multiplication. Oh, I think I mean multiplicative. That's what we're checking down here. D if the product is D of each of these things. Multiply together. So, oh my goodness. So d of beta is quite large, so d of alpha is less than that product. Oh my goodness, right, okay. I've kind of forgotten what we're doing. Oh my goodness, this is crazy. If instead we had to find... So this thing is smaller. It follows that, and then you can do this. What is going on? Oh, so you can do... This is like... to generate a sequence... Every other one... Right, hang on. Every other one... xn plus root 2yn. I think this must be a definition of xn plus root 2yn. It's just being this power thing. And it's taking, because it's multiplicative, it's taking the d, the norm of that thing, which is 1 minus 2 times 2, is... What? 1 minus 2 times 2 is minus 3. Coefficient b is 1 in this. I don't even calculate it here for me. I'm an idiot. 1 take away 2 is minus 1. Good. Read the text on the screen. Read the text on the screen. Good. Okay, so just giving us a way to generate these things using the norm. Ooh, it's a really weird norm. I want to explore this at some point. That should be a thing to do at some point, I suppose. A squared minus 2b squared, so this kind of like norm. Okay, we got a norm. We got some weird application of distance functions down here. A squared minus 2b squared to be the kind of size of that number in the ring integers with root 2. These things on the left, a plus b root 2, where a and b are integers. That thing is a really nice norm because it's multiplicative, which means that you can choose the right one that's got, so you choose some example of a number in z root 2 that has norm minus 1, then you can keep generating these things by like doing powers of that number to generate solutions alternately to those two equations. It's pretty cool. Okay, it's kind of unrelated to the Quintic, I think. All right, we've got one of these propositions that reminds me a lot of everything I used to know. R is a Euclidean domain and I is in R. Oh my goodness, then I is principal. I think this is going to be says that all ideals in ED are principal. So in an ED, irreducible elements are prime. Wow, okay, that's a good consequence. Oh, so in an Euclidean domain, irreducibles and primes are the same thing? I hope so. Here are some things that are not Euclidean domains. That's a shame. And over here we go for this, like, some load of maths about how the Euclidean algorithm works, which I happen to already know. So I'm sort of skipping how this works. And then that's good, because that'll get us down to, if we understand this, and don't actually calculate these higher close confactorations, we're getting down to PIDs over here, page 35. It's pretty good progress. Hi, Enjoy at RIP. This is rings and modules, which is going to be, I'll put it in chat as well. So I guess ring theory, which is part of, I think technically part of linear algebra. I don't know why I'm typing in chat as well. Never mind. Maybe. leading to well, the place we're trying to go to is Galois theory. That's where we want to be. Good. Well, I think someone in chat. What are the odds? The thing is related a lot to number theory, to later geometry, polynomials and stuff like that. Good. I'm going to take a break though. So I had one viewer at the start and I had one viewer at the end. So I'm going to be back in about half an hour to look more at PID. Hey, thanks for following. I'm going to be back later to look more at principal ideal domains and Euclidean domains once I've had my lunch. Right, let's put that in chat as well. The joke is that this is kind of replacing my normal job for a week. So, like a normal job, I'm going to take lunch breaks. I assume this is how streaming normally works. Good. Thanks for joining me on a morning of learning about ring theory. The quest continues. Quick look at the map. We started out, there's our notes that we've got so far. I started out with groups and vectors. We've made a little bit of progress along our route into kind of the mountains of ring theory. That's where we're going. So I guess I can move the little stick figure along like this. Just starting to get into ring theory. Actually, more like in the mountains. There we go. Just starting to get into ring theory. We've seen the field extensions. And ahead there is all this sort of Galois theory before we can get to the Quintic over there, the kind of distant space. Along the way so far, I've realised that I remember more ring theory than I thought, so that's good for me. And I've realised we're using a lot more vector spaces. They've turned up more than I thought they would. So at some point, if I try and turn this into a version where I'm explaining it so that, you know, if I'm teaching this at some point, then I'd have to teach vector spaces first. I guess that's obvious. That's just how maths degrees are structured. Cool, right, back in half an hour. Have a break. It's really silly. I've just gained a viewer. I've got one viewer, and now I'm off. Bye. Right, the quest is to be continued. Half an hour. Take care. Bye.